Good evening, and welcome to the Nocturnal Astronomer. I'm Atlas Reid, and I'll be your guide on this journey through our cosmic neighborhood. Over the next 8 episodes, we're going to drift peacefully from one world to another, exploring each planet in our solar system. From the scorched surface of Mercury, closest to our Sun, all the way out to the ice giant Neptune at the edge of our planetary family, each story will take you on a gentle voyage of discovery. You'll float above crimson Martian canyons, glide through Jupiter's swirling storms, and dance among Saturn's glittering rings. We'll visit rocky worlds and gas giants, explore moons and mysteries, all while your mind relaxes and your breathing slows. These aren't just tales about distant spheres of rock and gas. They're invitations to wonder, crafted to carry you softly toward dreams while you discover the beauty that surrounds our small blue home. If you enjoy drifting off to sleep with the stars, give this video a thumbs up and subscribe to join us for future cosmic journeys. And here's something fun. In the comments below, if you could actually visit one of these planets, which one would you choose? Let's dive in. Mercury sits just 36 million miles from the Sun, making it the innermost planet in our solar system. To put that in perspective, if Earth were a basketball sitting 100 feet from a bonfire, Mercury would be a golf ball placed just 39 feet away. This proximity to our star defines everything about Mercury's character. The planet completes one orbit around the Sun every 88 Earth days, moving through space at a blistering speed of nearly 105,000 miles per hour. Ancient astronomers noticed how quickly Mercury appeared to move across the sky, which is precisely why they named it after the fastest of the Roman gods. Despite being the closest planet to the Sun, Mercury isn't actually the hottest planet in our solar system. That title belongs to Venus, whose thick atmosphere traps heat like a blanket. Mercury, by contrast, has almost no atmosphere to speak of, which creates the most extreme temperature swings in the solar system. During the day, when the sun beats down on Mercury's surface, temperatures can soar to 800 degrees Fahrenheit, hot enough to melt lead. But without an atmosphere to hold that heat, nighttime temperatures plummet to minus 290 degrees Fahrenheit. That's a temperature difference of over 1,000 degrees, like going from the inside of an oven to far colder than any winter on Earth, all in one day. Mercury is small, only slightly larger than Earth's moon. With a diameter of just 3,030 miles, you could fit about 18 Mercuries inside Earth. If you could stand on Mercury's surface, you'd weigh only about 38% of what you weigh on Earth. A person weighing 150 pounds on Earth would weigh just 57 pounds on Mercury. This low gravity is a consequence of Mercury's small size and, as we'll discover later, its unusual composition. The planet spins very slowly on its axis, taking 59 Earth days to complete one rotation. This slow spin, combined with its fast orbit, creates a peculiar situation. A single day on Mercury, from one sunrise to the next, actually lasts 176 Earth days. That means a Mercury year is only 88 days long, but a Mercury day is 176 days long. In other words, 2 Mercury years pass in the time it takes for one complete day and night cycle. Mercury has been known to humanity since ancient times, visible to the naked eye as a bright point of light that appeared near the horizon just after sunset or just before sunrise. The ancient Sumerians wrote about Mercury as early as the 3rd millennium BCE, calling it Nabu after their god of wisdom and writing. The ancient Greeks actually thought Mercury was 2 different celestial bodies, calling the morning appearance Apollo and the evening appearance Hermes. It wasn't until the time of Pythagoras, around the 5th century BCE, that Greek astronomers realized these were observations of the same wandering star. The challenge of observing Mercury has always been its proximity to the Sun. The planet never strays far from our star in the sky, appearing only during twilight hours when the sky is still somewhat bright. This makes detailed observation difficult. Ancient astronomers had to catch Mercury during those brief windows when it reached its greatest angular distance from the Sun, an event astronomers call greatest elongation. Even then, they were looking through thick layers of Earth's atmosphere near the horizon, which distorts and blurs the image. The invention of the telescope in the early 17th century promised new insights into Mercury's nature. Galileo Galilei observed Mercury through his primitive telescope beginning in 1610, though the planet's small size and proximity to the Sun made detailed study nearly impossible. He was able to observe that Mercury went through phases like our Moon, appearing as a crescent or gibbous shape depending on its position relative to Earth and the Sun. This observation was crucial evidence supporting the Copernican model of the solar system, which placed the Sun at the center rather than Earth. In the 1630s, Giovanni Zuppi made the first telescopic observations that confirmed Mercury showed phases, definitively proving that Mercury orbited the Sun and not Earth. Throughout the 17th and 18th centuries, astronomers continued making incremental improvements in their understanding of Mercury. They refined measurements of its orbital period and began attempting to map surface features, though these early maps were largely speculative and inaccurate due to the difficulty of observation. The 19th century brought a mystery that would puzzle astronomers for decades. In 1859, a French mathematician discovered that Mercury's orbit didn't behave quite as Newton's laws of gravity predicted. The point of Mercury's closest approach to the Sun, called perihelion, slowly shifted position over time. This shift, called perihelion precession, occurs for all planets, but Mercury's precession was faster than could be explained by the gravitational influence of other planets. It was calculated that Mercury's perihelion advanced by about 43 arc-seconds per century more than Newton's theory predicted. This tiny discrepancy might seem insignificant, but in science, when observations don't match theory, it usually means something interesting is going on. Some astronomers proposed the existence of another planet, which they named Vulcan, orbiting even closer to the Sun than Mercury. Observers even claim to have spotted this hypothetical planet during solar eclipses. However, no such planet was ever confirmed to exist. The mystery of Mercury's orbit remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's new understanding of gravity, which described it not as a force but as a curvature of spacetime, perfectly predicted Mercury's orbital precession. The intense gravitational field near the Sun warped spacetime enough to cause Mercury's orbit to shift in exactly the way astronomers observed. This was one of the first major confirmations of general relativity and showed that Mercury, despite being small, was helping us understand the fundamental nature of the universe. Sometimes the smallest things reveal the biggest truths. When we look at Mercury through a telescope, even a powerful one, we see a world that resembles our Moon, covered in craters and lacking the obvious features like clouds or polar caps that mark other planets. But Mercury's surface tells a story billions of years old, written in impact scars, volcanic plains, and mysterious cliffs that stretch for hundreds of miles. The most obvious features on Mercury are its impact craters, created when asteroids and comets slammed into the surface. These craters range from tiny bowls just a few feet across to enormous basins hundreds of miles wide. The largest confirmed impact structure on Mercury is the Caloris Basin, a massive scar measuring roughly 960 miles across. To visualize this, imagine a crater so large that if it were placed over the eastern United States, it would stretch from New York to South Carolina. The impact that created Caloris was so powerful that it sent shock waves through the entire planet, creating strange, jumbled terrain on the opposite side of Mercury. When a large asteroid strikes a planet at cosmic speeds, typically tens of thousands of miles per hour, the impact releases energy equivalent to billions of nuclear bombs. The rock at the impact site instantly vaporizes, creating a blast wave that excavates a deep crater. On Mercury, many craters have bright rays extending outward from them, made of fresh material thrown out during the impact. These rays can stretch for hundreds of miles, like splash marks frozen in stone. Over time, exposure to solar radiation and micrometeorite impacts slowly darkens these rays, so bright rays indicate relatively young craters. Between the craters lie smooth plains that cover about 40% of Mercury's surface. For many years, scientists debated whether these plains were formed by ancient lava flows or by material ejected from impacts. Data from spacecraft missions has confirmed that these are indeed volcanic plains, similar to the Dark Maria on our moon. Billions of years ago, Mercury was volcanically active, with lava seeping up through cracks in the crust and flooding low areas. These lava flows buried older craters and created the relatively smooth surfaces we see today. The most peculiar geological features on Mercury are its enormous cliffs, called lobate scarps. These scarps can be over a mile high and stretch for hundreds of miles across the surface. Discovery Rupees, one of the largest known scarps, is about 400 miles long. These cliffs were created as Mercury's interior cooled and contracted. Think of what happens to a grape as it dries into a raisin. The skin wrinkles and folds as the interior shrinks. Mercury did something similar, but instead of wrinkles, its solid crust cracked and thrust upward, creating these massive scarps. Scientists estimate that Mercury's radius has shrunk by about 4 to 7 miles since the planet formed 4.5 billion years ago. That might not sound like much for a planet 3,000 miles wide, but it represents an enormous amount of contraction. This shrinking continues today, making Mercury a tectonically active world. Recent high-resolution images have revealed small scarps that appear to cut through small craters, suggesting these scarps formed relatively recently, perhaps within the last 50 million years. Mercury's surface is also covered in a fine dust called regolith, created by billions of years of meteorite impacts. Each impact, no matter how small, chips away at the surface rocks, grinding them into progressively finer powder. This regolith is extremely dark, reflecting only about 11% of the sunlight that hits it. Mercury is actually one of the darkest terrestrial planets, despite being so close to the Sun. For comparison, Earth's moon reflects about 12% of incoming sunlight, making it only slightly brighter than Mercury. If we could slice Mercury in half and look inside, we'd discover one of the most puzzling aspects of this small planet. Mercury has an enormous iron core that makes up about 61% of its volume. To understand how unusual this is, consider that Earth's iron core makes up only about 17% of its volume. If Earth had the same proportions as Mercury, our planet would be significantly smaller and much denser. Mercury is the second densest planet in the solar system, with only Earth being denser, and Earth's greater density is partly due to gravitational compression from its larger mass. Why does Mercury have such a disproportionately large core? This question has puzzled planetary scientists for decades, and several theories attempt to explain it. One possibility is that Mercury originally formed with more rocky material surrounding its core, but a catastrophic collision with another planet-sized body early in the solar system's history stripped away much of that rocky mantle, leaving the metal-rich core relatively exposed. This is similar to what scientists think happened to Earth when a Mars-sized body struck us, creating our moon. Another theory suggests that in the early solar system, when Mercury was still forming, the intense heat and solar wind from the young sun might have vaporized and blown away lighter rocky materials, leaving behind the heavier metallic elements that eventually formed Mercury's large core. Think of it like a cosmic winnowing process, where the sun's energy sorted materials by weight, allowing lighter elements to be pushed outward while heavier elements remained close in. A third possibility involves the chemistry of the early solar system. Different regions of the protoplanetary disk had different compositions, and the area where Mercury formed might have simply been richer in metallic elements. This would mean Mercury formed with its current proportions rather than losing material later. Each of these theories has evidence supporting it, and the truth might involve a combination of all three processes. Mercury's core is not entirely solid. Scientists believe it has a solid inner core surrounded by a liquid outer core, similar to Earth's structure. We know the outer core must be liquid because Mercury generates its own magnetic field, and the most common way to create a planetary magnetic field is through a dynamo effect in a liquid metallic core. As the planet rotates, the liquid iron in the core circulates, and these flowing electric currents create magnetic fields. However, Mercury's magnetic field is much weaker than Earth's, only about 1% as strong. This weak field still provides some protection from the solar wind, creating a small magnetosphere around the planet. The solar wind, a stream of charged particles flowing out from the sun, pushes against this magnetosphere, compressing it on the side facing the sun and stretching it into a tail on the night side, like a windsock in a breeze. Surrounding the core is a mantle made of silicate rocks, similar to the rock that makes up Earth's mantle but much thinner relative to the planet's size. This mantle is only about 260 miles thick, compared to Earth's mantle, which is about 1,800 miles thick. Above the mantle lies a crust estimated to be only 20 to 30 miles thick in most places. This thin crust is one reason why Mercury's ancient volcanic activity was able to bring lava to the surface relatively easily. Recent research suggests Mercury's core may be partially solid now, freezing from the inside out as the planet slowly cools. As liquid iron crystallizes onto the solid inner core, it releases heat and light elements that rise through the outer liquid core, driving the dynamo that creates Mercury's magnetic field. This process may have been going on for billions of years and could continue for billions more, though the magnetic field will likely continue to weaken as the core cools. When we think of a planetary atmosphere, we usually imagine something like Earth's thick blanket of air, or perhaps the crushing carbon dioxide atmosphere of Venus. Mercury's atmosphere, if we can even call it that, is nothing like these. It's so incredibly thin that scientists often call it an exosphere rather than an atmosphere. The entire exosphere contains only about 2,000 pounds of material. To put that in perspective, if you could gather all of Mercury's atmosphere and weigh it, it would weigh less than a small car. The atoms and molecules in Mercury's exosphere are so sparse that they rarely collide with each other. Instead, individual atoms follow ballistic trajectories, like tiny baseballs thrown upward, arcing through space before falling back to the surface under Mercury's weak gravity. The exosphere is constantly being stripped away by the solar wind and replenished by various processes we'll explore. An atom in Mercury's exosphere typically spends only about 3 hours aloft before either escaping to space or crashing back into the surface. So what is Mercury's exosphere made of? The composition is surprisingly varied and includes hydrogen, helium, oxygen, sodium, potassium, calcium, and magnesium. The proportions of these elements change over time and vary by location. Sodium and potassium are particularly interesting because they emit light at specific wavelengths that astronomers can detect from Earth. By observing this glow, scientists can study how Mercury's exosphere responds to changes in solar activity and the planet's position in its orbit. Where do these atoms come from? There are several sources. Some atoms, particularly hydrogen and helium, come directly from the solar wind. These light elements are constantly streaming away from the sun, and some get temporarily captured by Mercury's weak gravity. Other atoms are knocked off the surface by solar wind particles in a process called sputtering. Imagine tiny bullets hitting the surface and knocking off individual atoms. It's like using a sandblaster, but with charged particles instead of sand grains. Another source is photon-stimulated desorption, where intense ultraviolet light from the sun gives atoms on the surface enough energy to break free and leap into the exosphere. Additionally, micrometeorites constantly rain down on Mercury's surface. These impacts, though individually tiny, collectively vaporize surface material and loft atoms into the exosphere. It's been estimated that Mercury's surface receives about 3 times as many micrometeorite impacts as our Moon, due to Mercury's proximity to the Sun and the gravitational influence of the Sun focusing incoming material. Mercury's exosphere also interacts with the planet's magnetic field and the solar wind in complex ways. During magnetic storms on the Sun, the increased solar wind pressure can compress Mercury's magnetosphere, allowing more solar wind particles to reach the surface and increasing the rate of sputtering. This creates temporary enhancements in the exosphere, particularly on the day side of the planet. Sodium atoms, being relatively heavy, tend to accumulate in a tail extending away from the Sun, creating a faint comet-like feature that astronomers can sometimes detect from Earth. Temperature plays a crucial role in the behavior of Mercury's exosphere. On the scorching day side, where surface temperatures reach 800 degrees Fahrenheit, more atoms have enough thermal energy to escape from the surface. On the frigid night side, where temperatures plunge to minus 290 degrees, atoms tend to stick to the surface and freeze out. This creates a day-night asymmetry in the exosphere, with the day side having a much denser exosphere than the night side. The study of Mercury's exosphere helps scientists understand similar processes occurring on other airless bodies in the solar system, including our Moon, and provides insights into how planetary atmospheres evolve over time. Mercury represents an extreme case, where an atmosphere is continuously being lost and replenished, never reaching equilibrium, always changing. Mercury's orbit around the Sun is one of the most eccentric among the planets, meaning its path is noticeably elliptical rather than circular. At its closest approach to the Sun, called perihelion, Mercury comes within 29 million miles of our star. At its farthest point, called aphelion, Mercury reaches 43 million miles away. This means Mercury's distance from the Sun varies by about 14 million miles during each orbit, a difference of nearly 50%. This eccentric orbit has profound effects on Mercury's environment. When Mercury is at perihelion, it receives about 2.5 times more solar radiation than when it's at aphelion. Imagine the difference between standing near a campfire and then moving several feet away. The heat you feel drops dramatically with distance, and the same principle applies to Mercury. The intensity of sunlight, and therefore the temperature on Mercury's surface, varies significantly throughout the planet's 88-day year. The relationship between Mercury's rotation and its orbit is one of the strangest in the solar system. Mercury is tidally locked to the Sun, but not in the way our Moon is tidally locked to Earth. Our Moon always shows us the same face because it rotates once per orbit. Mercury, however, rotates 3 times for every 2 orbits it completes. This 3-to-2 ratio is called a spin-orbit resonance, and it means that some parts of Mercury experience very different conditions than others. Here's where things get interesting. Because of this 3-to-2 resonance, there are 2 locations on Mercury's equator, exactly opposite each other, that experience the most extreme temperatures. These points, called the hot poles, face the Sun when Mercury is at perihelion, receiving maximum solar radiation. At these locations, the temperature can reach nearly 900 degrees Fahrenheit. Meanwhile, points located 90 degrees away in longitude, called the cold poles, face the Sun when Mercury is at aphelion and experience somewhat cooler maximum temperatures. The combination of Mercury's slow rotation and eccentric orbit creates bizarre effects for a hypothetical observer standing on the surface. From certain locations, you would see the Sun rise, stop, move backward across the sky, stop again, and then continue forward before setting. This happens because Mercury's orbital speed varies according to Kepler's laws. When Mercury is closest to the Sun, it moves faster in its orbit, and this increased orbital motion can temporarily exceed the rate of the planet's rotation, causing the Sun to appear to move backward. Another consequence of the 3-to-2 resonance is that different parts of Mercury's surface experience dramatically different numbers of sunrises. If you stood at one of the hot poles and watched for 2 Mercury years, you would see just 1 sunrise and 1 sunset. Meanwhile, standing at certain other longitudes, you would see the Sun rise, reverse course and set, then rise again and set again, all during the same Mercury day. Scientists believe Mercury's unusual rotation rate is a result of tidal forces from the Sun acting on the planet over billions of years. Just as Earth's gravity raised tides on Mercury and gradually slowed its rotation, the Sun's gravity acted on slight asymmetries in Mercury's mass distribution, eventually locking the planet into its current 3-to-2 resonance. This process, called tidal despinning, affects all planets and moons, though the final state depends on the specific characteristics of each body. Mercury's orbit also precesses, meaning the orientation of the orbit slowly rotates over time. This precession occurs for all planets due to the gravitational influence of other planets, but Mercury's precession includes an extra component that could only be explained by Einstein's general theory of relativity. This small but measurable effect made Mercury crucial in confirming one of the most important theories in modern physics. One of the most surprising discoveries about Mercury came in the early 1990s when astronomers using Earth-based radar detected bright, radar-reflective patches at Mercury's north and south poles. These patches had characteristics consistent with water ice, a discovery that seemed absurd given that Mercury is the closest planet to the Sun. How could ice exist on a world where daytime temperatures can melt lead? The answer lies in Mercury's unusual orientation and the permanent shadows that exist in deep craters near the poles. Mercury's rotational axis is nearly perpendicular to its orbital plane, tilted by only about 2 degrees. Earth, by contrast, has an axial tilt of 23.5 degrees, which gives us our seasons. Mercury's minimal tilt means that the Sun always stays close to the horizon at the polar regions, and the floors of deep craters never receive direct sunlight. These permanently shadowed regions act as cold traps, where temperatures remain cold enough to preserve water ice for billions of years. Even though Mercury's equator bakes under intense solar radiation, the poles stay in eternal darkness, maintaining temperatures as low as -370 degrees Fahrenheit. This is cold enough to freeze carbon dioxide, not just water. The evidence for water ice at Mercury's poles became even stronger when NASA's MESSENGER spacecraft orbited Mercury from 2011 to 2015. MESSENGER's neutron spectrometer detected elevated hydrogen concentrations in the polar regions, consistent with water ice. The spacecraft's laser altimeter measured the reflectance of the polar deposits, finding they matched the properties of water ice mixed with a darker material, possibly organic compounds. Scientists estimate there may be between 100 billion and 1 trillion metric tons of water ice in Mercury's polar regions. That sounds like an enormous amount, and in absolute terms it is, but it's concentrated in areas of permanent shadow within craters. Some of this ice may be relatively pure, particularly in the coldest areas, while other deposits appear to be covered by or mixed with darker material that may be organic-rich compounds. Where did this ice come from? The most likely sources are comets and asteroids that have struck Mercury over billions of years. Comets are essentially dirty snowballs, containing significant amounts of water ice along with dust and organic compounds. When a comet impacts Mercury, most of the water vaporizes in the intense heat of the impact and is lost to space. However, some water molecules bounce around the surface until they eventually migrate to the permanently shadowed polar regions, where they freeze and accumulate. Micrometeorites also continuously deliver small amounts of water to Mercury. Though each micrometeorite carries only a tiny amount of water, over billions of years, these impacts add up. Some scientists have also proposed that chemical reactions between hydrogen from the solar wind and oxygen-bearing minerals on Mercury's surface could produce water molecules, though this is likely a minor source compared to cometary delivery. The discovery of ice on Mercury has important implications beyond understanding this one planet. It tells us that even in the most unlikely places, water can find refuges where it persists. Similar cold traps exist at the lunar poles, and indeed, ice has also been detected on our moon. This is important for future space exploration because water is a precious resource. It can be broken down into hydrogen and oxygen, providing fuel and breathable air, and of course it's essential for human consumption. Mercury's ice also preserves a record of the solar system's history. The water molecules frozen in those permanently shadowed craters have been locked away for potentially billions of years, protected from the sun's radiation and heat. Studying these ancient ices could tell us about the composition of early comets and asteroids, the history of water delivery in the inner solar system, and even provide clues about the ingredients that made Earth's oceans. Sending spacecraft to Mercury is one of the most challenging endeavors in space exploration. The planet's proximity to the Sun creates intense thermal and radiation environments that can damage spacecraft systems. Additionally, reaching Mercury requires tremendous amounts of energy. Counterintuitively, it's actually harder to send a spacecraft to Mercury than to send one to Mars, even though Mercury is closer to Earth. This is because of the Sun's immense gravitational pull. When a spacecraft leaves Earth, it's already moving around the Sun at Earth's orbital speed of about 67,000 miles per hour. To reach Mercury, which orbits much closer to the Sun, the spacecraft must lose a tremendous amount of this orbital energy. It's like trying to slow down a speeding car, requiring enormous amounts of fuel or clever orbital mechanics using planetary flybys. The first spacecraft to visit Mercury was NASA's Mariner 10, which made 3 flybys of the planet in 1974 and 1975. Mariner 10 discovered Mercury's magnetic field, took the first close-up images of the surface, and measured the planet's basic physical properties. The spacecraft used a gravity assist from Venus to help it reach Mercury, pioneering a technique now commonly used for deep space missions. During its 3 encounters, Mariner 10 mapped about 45% of Mercury's surface at resolutions far better than any Earth-based telescope could achieve. However, after Mariner 10, Mercury remained unvisited for more than 3 decades. The technical challenges and high costs of a Mercury mission meant other targets received priority. This changed in 2004 when NASA launched the Messenger spacecraft, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging. Messenger took a complex route to Mercury, performing 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys before finally entering orbit around the planet in March 2011. Messenger spent 4 years orbiting Mercury, revolutionizing our understanding of the planet. The spacecraft carried 7 scientific instruments that studied Mercury's surface composition, mapped the planet's magnetic field, measured the exosphere, and took thousands of high-resolution images. Messenger confirmed the presence of water ice at the poles, discovered that Mercury's surface contained surprisingly high amounts of volatile elements like sulfur, and found evidence for relatively recent volcanic activity. One of Messenger's most important contributions was completing a global map of Mercury's surface. For the first time, scientists could see the entire planet in detail, not just the 45% mapped by Mariner 10. These images revealed additional huge impact basins, extensive volcanic plains, and numerous examples of the planet's unusual tectonic features. The spacecraft also discovered that Mercury's magnetic field is offset from the planet's center, shifted northward by about 300 miles, a peculiarity that scientists are still working to explain. Messenger's mission ended in April 2015 when the spacecraft, having exhausted its fuel, was deliberately crashed into Mercury's surface at over 8,000 miles per hour. The impact created a new crater about 50 feet across, adding one final mark to the planet Messenger had studied so thoroughly. This controlled crash was carefully planned to occur on the far side of Mercury, where it wouldn't damage any scientifically interesting regions. The next mission to Mercury is BepiColombo, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, launched in 2018. BepiColombo consists of 2 spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, which will separate upon arrival and study Mercury from different perspectives. The mission is taking a long route to Mercury, using gravity assists from Earth, Venus, and Mercury itself to gradually adjust its trajectory. BepiColombo is scheduled to enter orbit around Mercury in 2025, where it will study the planet for at least 1 year, with possible extensions. The mission carries a suite of instruments designed to build on Messenger's discoveries, including high-resolution cameras, spectrometers to study surface composition, magnetometers to map the magnetic field in detail, and instruments to study the exosphere and magnetosphere. Mercury formed 4.5 billion years ago from the same disk of gas and dust that gave birth to the Sun and all the other planets. In the early solar system, the region close to the Sun was extremely hot enough that only materials with high melting points, like metals and rocky minerals, could remain solid. Lighter, more volatile materials like water ice and organic compounds were vaporized by the intense heat and pushed outward by solar radiation and the solar wind, which is why the inner planets, Mercury, Venus, Earth, and Mars, are all rocky while the outer planets are gas and ice giants. Small particles of metal and rock in the inner solar system began sticking together through collisions, gradually building up larger and larger bodies called planetesimals. These planetesimals, ranging from miles to hundreds of miles across, continued colliding and merging in a violent process called accretion. Over millions of years, a few dominant bodies emerged, sweeping up most of the material in their orbital zones and becoming the terrestrial planets we know today. The early solar system was a chaotic place, with planetary embryos and leftover planetesimals careening through space on intersecting orbits. Mercury likely suffered numerous giant impacts during this period, collisions energetic enough to melt the entire planet and perhaps strip away portions of its mantle, which might explain its unusually large iron core. Some scientists think Mercury might have originally formed farther from the Sun and later migrated inward due to gravitational interactions with other planets and the protoplanetary disk. Once Mercury reached approximately its current size, the planet began to cool. The interior was initially molten throughout, but over millions of years, heat radiated away into space, and the planet began to solidify from the outside in. As the interior cooled and contracted, Mercury's crust cracked and formed the giant scarps we see today. Volcanic activity, powered by heat from the interior and radioactive decay, continued for billions of years, creating the smooth plains that cover much of the surface. About 3.8 billion years ago, the inner solar system experienced a period called the Late Heavy Bombardment, when a sudden increase in asteroid and comet impacts pummeled the terrestrial planets and their moons. Evidence for this bombardment is preserved in the heavily cratered surfaces of the Moon, Mars, and Mercury. The Caloris Basin and other large impact structures on Mercury likely formed during this violent period. After the late heavy bombardment ended, impact rates decreased to roughly their current levels, and Mercury's volcanic activity gradually ceased as the planet's interior continued to cool. For the past 3 billion years or so, Mercury's surface has been relatively stable, modified primarily by occasional impacts and the slow contraction of the planet as its interior continues to cool. The small scarps that cut through relatively young craters tell us that this contraction is still happening today, making Mercury one of the few tectonically active terrestrial bodies in the solar system. What does the future hold for Mercury? For billions of years to come, Mercury will continue orbiting the Sun much as it does now. The planet will continue to slowly cool and contract. Its core will gradually solidify, eventually shutting down the magnetic field. The exosphere will continue its endless cycle of loss and replenishment. Micrometeorites will keep grinding the surface into ever finer dust. The ice-hidden and permanently shadowed craters will remain frozen, a cold archive in a scorched world. In the very distant future, about 5 billion years from now, the Sun will exhaust its hydrogen fuel and begin fusing helium, expanding into a red giant. As the Sun swells, it will likely engulf Mercury entirely, vaporizing the planet that spent its existence closest to our star. But that fate lies so far in the future that the time span is almost meaningless on human scales. For now, Mercury continues its eternal dance, a small gray world circling our Sun, keeping secrets in its iron heart and ice-filled craters, a reminder that even the most familiar neighborhood, our solar system, still holds mysteries waiting to be understood. And on that note, we've completed our journey through Mercury, from its ancient discovery to its distant future, from its scorching surface to its frozen poles, from its enormous iron core to its wispy exosphere. This small planet, so often overlooked in favor of more dramatic worlds, reveals itself to be a place of extremes and surprises, a natural laboratory where we can study planetary processes pushed to their limits. Thank you for joining me on this voyage through the innermost realm of our solar system. Venus has captivated humanity for thousands of years. Ancient civilizations tracked its movements across the sky with remarkable precision. The Maya calculated the Venus cycle to within hours over centuries of observation. The Babylonians kept detailed astronomical diaries that tracked Venus alongside the Moon and other planets. To the naked eye, Venus outshines every celestial object except the Sun and Moon. This brilliance comes from Venus's thick atmosphere and its proximity to Earth. At its closest approach, Venus comes within about 38 million kilometers of our planet, closer than any other planet in the solar system. The clouds that envelope Venus reflect about 75% of the sunlight that reaches it, making it extraordinarily bright. This reflectivity, called albedo, is higher than any other planet. For much of human history, people didn't realize that the morning star and evening star were the same object. The ancient Greeks initially called the morning appearance Phosphorus and the evening appearance Hesperus. Eventually, they recognized these were a single wandering star, which they named Aphrodite. The Romans later renamed it Venus, after their goddess of love and beauty. The planet's beauty from afar stands in stark contrast to its actual nature. Venus is almost exactly the same size as Earth, with a diameter of about 12,100 kilometers compared to Earth's 12,742 kilometers. It has about 82% of Earth's mass. This similarity in size and composition is why Venus earned the nickname Earth's twin. But that's where the similarities end. Venus orbits the Sun at an average distance of about 108 million kilometers, roughly 72% of Earth's distance from the Sun. It completes one orbit every 224.7 Earth days. But here's where things get strange. Venus rotates on its axis incredibly slowly, taking about 243 Earth days to complete one rotation. This means a day on Venus is actually longer than its year. Even more peculiar, Venus rotates backwards compared to most planets in our solar system. While Earth and most other planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. This retrograde rotation remains something of a mystery. Scientists theorize that a massive collision early in Venus's history might have flipped it over, or that gravitational interactions with the Sun over billions of years gradually reversed its spin. The slow rotation has profound effects on Venus's environment. On Earth, our relatively rapid rotation helps generate our magnetic field through the dynamo effect in our planet's molten core. Venus, rotating so slowly, generates no significant magnetic field. This leaves the planet vulnerable to the solar wind, the stream of charged particles flowing from the Sun. Without a magnetic shield, the solar atmosphere directly interacts with Venus's upper atmosphere, slowly stripping it away into space. From our perspective on Earth, Venus never strays far from the Sun in the sky. It reaches a maximum elongation, or angular distance from the Sun, of about 47 degrees. This means we can only see Venus in the hours around sunrise or sunset. For ancient observers, this dance with the Sun added to Venus's mystique and importance in various mythologies and early astronomical systems. The atmosphere of Venus is one of the most extreme environments in our solar system. Standing on the surface of Venus, you would experience atmospheric pressure 92 times greater than Earth's sea level pressure. To put this in perspective, this is equivalent to the pressure you'd feel if you dove about 900 meters beneath Earth's oceans. The weight of all that atmosphere pressing down would be immediately noticeable. This crushing atmosphere consists of about 96.5% carbon dioxide. The remaining few percent includes nitrogen and trace amounts of other gases. The density of this atmosphere is about 67 times that of Earth's atmosphere. If you could somehow survive on Venus's surface, moving through this atmosphere would feel more like wading through water than walking through air. The temperature at the surface averages about 467 degrees Celsius, or 873 degrees Fahrenheit. This is hot enough to melt lead, which melts at 327 degrees Celsius. Remarkably, this temperature remains nearly constant across the entire planet. The equator and the poles, the day side and the night side, all maintain this hellish temperature. The thick atmosphere acts like a blanket, redistributing heat so efficiently that temperature variations are minimal. This extreme greenhouse effect is what makes Venus so incredibly hot. Although Venus receives only about twice the sunlight that Earth does, its temperature is far higher than Mercury's, despite Mercury being much closer to the Sun. The carbon dioxide traps infrared radiation trying to escape from the surface, causing temperatures to build up over time. It's like parking a car in the sun with the windows rolled up, except on a planetary scale and far more extreme. The clouds of Venus form a permanent layer about 45 to 70 kilometers above the surface. These aren't water clouds like Earth's. They're composed primarily of sulfuric acid droplets. Sulfuric acid is the same corrosive substance used in car batteries. These clouds are so thick and extensive that they completely hide the surface from view. No telescope from Earth or even from orbit around Venus can see through these clouds using visible light. These sulfur compounds likely come from volcanic activity on Venus's surface. When sulfur dioxide is released by volcanoes, it rises into the atmosphere where ultraviolet light from the sun breaks it apart and allows it to combine with water vapor, forming sulfuric acid. The acid droplets form clouds that eventually produce rain. However, this rain never reaches the surface. The intense heat in the lower atmosphere causes the sulfuric acid raindrops to evaporate long before they could fall to the ground. The atmosphere displays another fascinating feature. The clouds race around the planet in just 4 Earth days, even though the solid planet below rotates once every 243 days. This phenomenon, called superrotation, means the atmosphere moves about 60 times faster than the planet's surface. Imagine if Earth's winds constantly blew at over 400 kilometers per hour. Scientists are still working to fully understand what drives this superrotation. High-altitude winds on Venus reach speeds of about 350 kilometers per hour near the equator. These winds decrease with altitude. At the surface, winds are sluggish, moving at only a few kilometers per hour. The thick atmosphere and slow rotation create a very different weather pattern than Earth's. While Earth has complex systems with high and low pressure areas that move around, Venus's weather is dominated by these high-altitude winds circling the planet. For centuries, the surface of Venus remained a complete mystery, hidden beneath its impenetrable cloud deck. Early science fiction writers imagined Venus as a world of steamy jungles and perhaps even dinosaurs, assuming that more sunlight would create a warmer, wetter version of Earth. The reality turned out to be far different and far more alien. Our first glimpses of Venus's surface came from Soviet Venera landers in the 1970s and early 1980s. These spacecraft provided the first and still the only photographs taken from the surface of Venus. The images showed a rocky, barren landscape bathed in an orange glow from sunlight filtering through the clouds. Flat stones and rocks scattered across the surface suggested volcanic activity. The landers survived only briefly, from about 23 minutes to just over 2 hours, before succumbing to the extreme heat and pressure. Later, radar mapping from NASA's Magellan spacecraft in the early 1990s revealed Venus's surface in unprecedented detail. Radar can penetrate the clouds, bouncing off the surface below and creating detailed maps. What these maps showed was a world dominated by volcanic features. About 80% of Venus's surface consists of volcanic plains, smooth areas formed by lava flows. Venus has tens of thousands of volcanoes, far more than Earth. Most are shield volcanoes, broad, gentle slopes similar to those found in Hawaii. Some of these shield volcanoes are enormous. Mont Mons, the tallest volcano on Venus, rises about 8 kilometers above the surrounding plains. While not as tall as Mars's Olympus Mons, it's still taller than any mountain in the lower 48 United States. Venus also features unique volcanic structures not found on Earth. Pancake domes are circular, flat-topped features formed when thick, viscous lava oozes out and spreads into a circular shape before hardening. Some of these pancake domes measure up to 65 kilometers across. Another unique feature is arachnoids, circular to elongated structures with radial patterns that resemble spiders. These may form when magma rising from below pushes up the surface, creating fractures that radiate outward. Coronae are perhaps the most distinctive features on Venus. These are large circular structures, ranging from 150 to over 2,000 kilometers in diameter, surrounded by concentric ridges and troughs. Scientists believe coronae form when plumes of hot material rise from deep within Venus's mantle, pushing up the surface. As the plume spreads out beneath the crust, it creates these circular patterns. Over 500 coronae have been identified on Venus. The question of whether Venus is still volcanically active remains open. Several pieces of evidence suggest ongoing volcanism. Variations in sulfur dioxide levels in the atmosphere over time could indicate volcanic eruptions releasing fresh gas. Some surface features appear too fresh to be ancient, lacking the weathering and impact craters you'd expect on very old surfaces. Recent analysis has suggested possible active lava flows, though this remains debated. Venus has relatively few impact craters compared to Mercury, Mars, or the Moon. Scientists have identified fewer than 1,000 craters on Venus. This suggests the surface is relatively young in geological terms, perhaps only 300 to 500 million years old. Something resurfaced most of Venus in the relatively recent past. This could have been a period of intense volcanic activity that covered older surfaces with fresh lava. The distribution of craters is remarkably uniform across Venus. Unlike Earth, where plate tectonics creates areas of different ages, Venus's craters are spread evenly. This suggests the resurfacing event or events affected the entire planet rather than occurring in stages across different regions. Understanding this resurfacing remains one of the major questions in Venus science. One of the most profound questions about Venus concerns water. Today, Venus is the driest known planet in our solar system. The atmosphere contains only about 30 parts per million of water vapor, compared to Earth's atmosphere, which averages about 10,000 parts per million. The entire planet has less water than exists in just a small section of one of Earth's oceans. But Venus wasn't always this way. Scientists have found compelling evidence that Venus once had significantly more water, possibly even oceans covering much of its surface. This evidence comes from studying the ratio of different hydrogen isotopes in Venus's atmosphere. Hydrogen comes in different forms, or isotopes. Regular hydrogen has just one proton in its nucleus. Deuterium, sometimes called heavy hydrogen, has one proton and one neutron. On Venus, the ratio of deuterium to regular hydrogen is about 150 times higher than on Earth. This enrichment in deuterium tells a story of loss. Water molecules containing regular hydrogen are lighter and can more easily escape into space when they reach the upper atmosphere. Water molecules containing deuterium are heavier and more likely to remain. Over billions of years, as Venus lost its water to space, the ratio of deuterium to hydrogen increased dramatically. By working backwards from this ratio, scientists estimate that Venus may have once had enough water to cover the planet in an ocean about 25 meters deep. Some models suggest even more water, enough for a global ocean 300 meters deep or even deeper. While this is far less than Earth's oceans, which average about 3,700 meters deep, it would have been enough to dramatically change Venus's environment. What happened to Venus's water? The story begins with the Sun. In its early history, the Sun was about 30% dimmer than today. As the Sun aged and fusion in its core became more efficient, it grew brighter. This increasing solar output gradually heated both Earth and Venus. Earth, being farther from the Sun, warmed to pleasant temperatures that allowed liquid water to persist. Venus, being closer, crossed a critical threshold. As Venus warmed, more water evaporated into the atmosphere. Water vapor is itself a greenhouse gas, trapping heat. This created a runaway greenhouse effect. More heat caused more evaporation, which trapped more heat, which caused more evaporation. Eventually, temperatures climbed so high that the oceans completely evaporated. Venus entered what scientists call a moist greenhouse state, with the atmosphere full of water vapor. In the upper atmosphere, ultraviolet radiation from the Sun broke apart water molecules through a process called photodissociation. The oxygen atoms combined with other elements in rocks and the atmosphere, getting locked away. The hydrogen atoms, being very light, escaped into space. Without a magnetic field to protect it, Venus's atmosphere was vulnerable to the solar wind, which helped strip away the hydrogen. This process took hundreds of millions or even billions of years, but eventually Venus lost most of its water. The carbon dioxide that had been dissolved in the oceans was released into the atmosphere. Volcanic activity continued to add more carbon dioxide. Without water or life to recycle carbon dioxide like Earth's ocean and plants do, the carbon dioxide accumulated, creating the thick atmosphere we see today. The timing of Venus's water loss remains debated. Some scientists think Venus lost its water very early in its history, perhaps within the first billion years. Others think Venus might have retained water much longer, possibly until 2 billion years ago or even more recently. The answer has profound implications for whether Venus could have supported life during its wetter phase. Understanding Venus's transformation from a potentially habitable world to the hothouse we see today helps us understand Earth's climate and the search for life on planets around other stars. The climate of Venus represents one of the most extreme transformations possible for a terrestrial planet. While Earth and Venus likely started with similar conditions, they diverged into radically different worlds. Understanding how and why this happened helps us appreciate both the fragility and resilience of planetary climates. The greenhouse effect on Venus operates on a scale difficult to fully grasp. Greenhouse gases in an atmosphere allow visible light from the Sun to pass through but trap infrared radiation trying to escape back into space. On Earth, this natural greenhouse effect warms our planet by about 33 degrees Celsius, making it habitable. Without it, Earth's average temperature would be well below freezing. On Venus, the greenhouse effect adds about 500 degrees Celsius to the surface temperature. Think of Venus's atmosphere as a tremendously thick blanket wrapped around the planet. Sunlight penetrates the clouds, though only about 25% reaches the surface. This light warms the rocks, which then emit infrared radiation. But this infrared radiation can't escape. The carbon dioxide molecules absorb it, heating the atmosphere. The hot atmosphere radiates energy both up and down, warming the surface even more. The clouds add another layer of complexity. Sulfuric acid droplets in the clouds reflect most incoming sunlight back into space, which actually keeps Venus cooler than it would otherwise be. Without these reflective clouds, Venus would be even hotter. The clouds also scatter light, creating the eerie orange glow visible in images from the surface. At the surface, the thick atmosphere scatters so much light that there are no sharp shadows. The illumination is diffuse and even, like an overcast day on Earth, but far more extreme. Temperature variations on Venus are remarkably small. The equator and poles differ by only a few degrees. Day and night are virtually identical in temperature. This happens because the thick atmosphere redistributes heat so efficiently. It would take an enormous amount of energy to cool any part of Venus's surface, more than can be lost during its long night. The heat capacity of the atmosphere, its ability to store thermal energy, combined with circulation patterns, ensures temperatures remain constant. Atmospheric circulation on Venus differs dramatically from Earth. On Earth, the temperature difference between equator and poles drives large-scale circulation patterns. Hot air rises at the equator, travels toward the poles at high altitude, sinks at the poles, and returns toward the equator at low altitude. These Hadley cells, as they're called, organize Earth's climate into zones. Venus has a single Hadley cell in each hemisphere. Air heated at low latitudes rises, travels toward the poles at high altitude, sinks at the poles, and returns toward the equator at lower altitude. But because temperature differences are so small, this circulation is driven more by the slow rotation and heating patterns than by temperature gradients. The super-rotating winds, moving much faster than the planet itself, dominate the circulation. At the poles, Venus displays a remarkable feature called a polar vortex. Similar to but more pronounced than Earth's polar vortices, Venus's polar vortex creates a strange double-eye pattern when viewed from above. The atmospheric circulation spirals down toward the pole, creating swirling clouds in a pattern that resembles a hurricane. The temperature at Venus's poles is actually slightly higher than at the equator, opposite to what we see on Earth, because descending air compresses and warms. The lower atmosphere is relatively calm. At the surface, winds blow at only about a meter per second, slower than a leisurely walk. The air is so dense that even these slow winds exert significant force, similar to ocean currents on Earth. Visibility at the surface would be limited to a few hundred meters by the thick, hazy atmosphere. Exploring Venus has proven to be one of the most difficult challenges in planetary science. The combination of crushing pressure, corrosive atmosphere, and extreme heat destroys conventional spacecraft within hours. Despite these challenges, humanity has sent dozens of missions to Venus, achieving remarkable successes and gaining invaluable insights into our sister planet. The Soviet Union's Venera program remains the most successful series of Venus landers. Between 1961 and 1984, the Soviets launched multiple missions to Venus. The early missions failed or provided only limited data, but gradually Soviet engineers developed techniques to survive Venus's environment. They built spacecraft with thick pressure vessels, cooling systems, and reinforced electronics. Venera 7 became the first spacecraft to successfully transmit data from the surface of another planet when it landed on December 15, 1970. It survived for 23 minutes before succumbing to the heat. Venera 7 confirmed the extreme surface temperature and pressure that scientists had suspected but not yet proven. This was a monumental achievement in space exploration. Later Venera missions improved on this success. Venera 9 and 10, which landed in 1975, carried cameras and returned the first black and white images from Venus's surface. The images showed a rocky surface with flat stones, suggesting volcanic activity. Venera 13 and 14 landed in 1982 and returned the first color images. These showed an orange-tinted landscape with scattered rocks and what appeared to be volcanic soil. These Soviet landers also analyzed the soil composition using X-ray fluorescence spectrometers. The results showed that Venus's rocks are similar to volcanic basalt found on Earth, confirming that Venus is geologically similar to our planet in composition. Some landers also detected possible lightning during their descent, though this remains controversial and debated among scientists. NASA's Pioneer Venus mission arrived in 1978 and consisted of an orbiter and multiple atmospheric probes. The orbiter mapped the surface using radar, providing the first global view of Venus's topography. The atmospheric probes measured the composition, temperature, and pressure at different altitudes and locations. These missions revealed details about the cloud layers and the extreme greenhouse effect. The most detailed mapping of Venus came from NASA's Magellan spacecraft, which orbited Venus from 1990 to 1994. Using synthetic aperture radar, Magellan mapped 98% of Venus's surface with a resolution better than 100 meters in most places. The data revealed the extensive volcanic features, the coronae, the impact craters, and the relatively young surface age. Magellan's maps remain the primary source of information about Venus's topography. European Space Agency's Venus Express orbited the planet from 2006 to 2014, studying the atmosphere in detail. Venus Express discovered the unusual double vortex at the South Pole and tracked changes in atmospheric composition over time. The spacecraft detected a possible sign of active volcanism when sulfur dioxide levels increased temporarily, though this interpretation remains debated. Japan's Akatsuki orbiter, which entered orbit around Venus in 2015 after a failed first attempt, continues to study Venus's atmosphere and weather patterns. Akatsuki has revealed details about the superrotation and discovered planetary scale waves in the atmosphere. These waves ripple through the cloud tops, possibly influenced by surface topography. More missions are planned for the coming decade. NASA has selected 2 missions to Venus. Veritas will create high-resolution topographic maps and search for active volcanism. Da Vinci will send a probe through the atmosphere, analyzing composition and taking pictures during descent. European Space Agency has approved Envision, another orbiter that will study Venus's surface and interior. These missions, planned for launch in the late 2020s and early 2030s, will answer many outstanding questions about Venus. One of the most intriguing questions about Venus concerns its distant past. Could Venus have once been habitable? Could it have supported life? These questions have moved from speculation to serious scientific investigation as our understanding of Venus has deepened. Several billion years ago, conditions on Venus were likely very different. The young sun was dimmer, providing less heat. If Venus had water oceans at this time, the planet might have maintained temperatures suitable for liquid water at the surface. Climate models suggest that Venus could have remained habitable for as long as 2 or 3 billion years after its formation, perhaps even longer. For Venus to have been habitable, several conditions would need to have been met. First, it would need liquid water at the surface. Second, temperatures would need to stay within the range where biochemistry as we understand it could function, roughly between 0 and 120 degrees Celsius. Third, the atmosphere would need to be much less dense and hot than today. Could Venus have maintained these conditions? Some climate models say yes. If early Venus had enough water, and if clouds formed over the oceans, these clouds could have reflected enough sunlight to keep the planet cool despite being closer to the sun. This is similar to how clouds on Earth reflect sunlight and cool the surface below them. The key factor would have been Venus's rotation rate. Today, Venus rotates extremely slowly, but it may have rotated faster in the past. Tidal interactions with the Sun could have gradually slowed its rotation over billions of years. A faster rotating Venus would have had different atmospheric circulation patterns, potentially supporting a more Earth-like climate. If Venus did rotate faster early in its history, it might have generated a magnetic field like Earth's. This magnetic field would have protected the atmosphere from the solar wind, helping Venus retain its water much longer. As the rotation slowed and the magnetic field disappeared, Venus would have become more vulnerable to atmospheric loss. The transition from habitable Venus to the hothouse we see today would have been gradual. As the Sun brightened and perhaps as Venus's rotation slowed, the planet would have warmed. More water would evaporate into the atmosphere. The greenhouse effect would strengthen. Eventually, the planet would cross a threshold where the oceans could no longer be maintained. This runaway greenhouse effect would have transformed the planet within a few 100 million years. Could life have emerged on early Venus? If the planet remained habitable for billions of years, it seems possible. Life emerged on Earth relatively quickly in geological terms, appearing within the first billion years of the planet's history. If Venus had similar conditions, there's no obvious reason life couldn't have emerged there as well. If life did emerge on Venus, what happened to it? When Venus lost its oceans and became the hothouse world we see today, any surface life would have perished. However, some scientists have speculated about the possibility of life surviving in the clouds. At altitudes around 50 to 60 kilometers above the surface, temperatures and pressures are much more moderate, similar to Earth's surface conditions. Recent controversial observations have suggested the possible detection of phosphine gas in Venus's atmosphere. Phosphine is a gas that on Earth is primarily produced by biological activity or industrial processes. The detection was disputed and remains unconfirmed. Even if phosphine exists in Venus's atmosphere, it could have non-biological explanations. Still, the possibility has renewed interest in the question of life on Venus. Understanding whether Venus was once habitable has implications beyond our solar system. Thousands of planets have been discovered around other stars. Many orbit closer to their stars than Earth orbits the Sun, placing them in what might be a Venus zone rather than a habitable zone. As we look toward the future, Venus continues to fascinate and challenge us. New missions planned for the coming decades promise to answer long-standing questions about our sister planet. Beyond scientific exploration, some visionaries have even contemplated the possibility of one day transforming Venus into a habitable world, though this remains far beyond our current capabilities. The upcoming missions to Venus represent a renaissance in Venus exploration after decades of relative neglect. NASA's Da Vinci mission will probe the atmosphere in unprecedented detail, measuring noble gas isotopes that will help us understand Venus's history. The mission will take the first high-resolution images of the Alpha Regio highlands during its descent, potentially revealing geological features that could indicate past water erosion. Veritas will use advanced radar to create three-dimensional maps of Venus's surface, revealing fine details and topography. It will also map the planet's infrared emissions, searching for heat signatures that would indicate recent or active volcanism. Understanding whether Venus is volcanically active today is crucial for understanding the planet's interior and how it differs from Earth. ESA's Envision mission will carry a suite of instruments to study Venus's surface and subsurface. It will search for changes in the surface over time, look for active geological processes, and study the interaction between the surface and atmosphere. Together, These 3 missions will provide a comprehensive view of Venus that we've never had before. Some scientists have proposed future missions that would include long-duration balloons floating in Venus's upper atmosphere where conditions are more moderate. These balloons could study the atmosphere for months or years, tracking weather patterns and searching for signs of chemistry that might indicate biological activity. Sample return missions, though extremely challenging, have also been proposed to bring pieces of Venus back to Earth for detailed analysis. Looking even further ahead, some researchers have contemplated the possibility of terraforming Venus, transforming it into a more Earth-like planet. This would be an enormous undertaking requiring technologies we don't currently possess. The basic idea would involve removing most of the carbon dioxide atmosphere and cooling the planet. Some proposals suggest using bacteria engineered to convert carbon dioxide into other forms, or constructing enormous sunshades to cool the planet. Other ideas involve seeding the atmosphere with chemicals that would react with the carbon dioxide, converting it into forms that would rain out onto the surface. Once cooled sufficiently, water could be imported from comets or other sources. Eventually, the thinking goes, Venus could be transformed into a second Earth. However, this remains purely theoretical. The energy required would be immense, and the timescales would span centuries or millennia. More realistic in the near term would be floating cities in Venus's upper atmosphere. At altitudes around 50 kilometers, the atmospheric pressure and temperature are similar to Earth at sea level. The carbon dioxide atmosphere below would provide buoyancy for habitats filled with oxygen and nitrogen, the same way helium balloons float in Earth's atmosphere. Solar panels would provide power, and the atmosphere itself could provide raw materials. Whether humanity will ever establish a presence at Venus remains to be seen. What is certain is that Venus will continue to teach us about planetary evolution, climate change, and the diversity of worlds in our solar system. Venus serves as a cautionary tale about greenhouse effects and shows us how a planet similar to Earth can evolve in dramatically different directions. The study of Venus also informs our search for life beyond our solar system. By understanding what makes a planet habitable or uninhabitable, we can better evaluate the thousands of worlds being discovered around other stars. Venus represents a crucial comparison point, showing us the boundaries of the habitable zone and helping us understand which distant worlds might harbor life. And on that note, our journey through Venus comes to an end. We've explored its hellish surface, traced the loss of its oceans, examined its extreme climate, and looked toward future missions that will reveal even more about this mysterious world. Picture, if you will, a massive cloud of gas and dust drifting through the galaxy, a nebula enriched with elements forged in the hearts of previous generations of stars. This solar nebula stretched across billions of kilometers, a cold, dark expanse where hydrogen and helium mixed with heavier elements like carbon, oxygen, and iron. This cloud wasn't uniform. Like cream swirling in coffee, denser pockets of material existed within the nebula. Scientists have determined through careful study of meteorites that something disturbed this peaceful cloud, perhaps the shock wave from a nearby supernova explosion. That disturbance triggered a process that would eventually lead to our existence. The cloud began to collapse under its own gravity, a slow, inexorable gathering of material that took millions of years to unfold. As the cloud collapsed, something interesting happened. The laws of physics dictated that as the material drew inward, it began to spin. Think of an ice skater pulling in their arms during a spin, rotating faster and faster. The solar nebula behaved in much the same way. As it contracted, its rotation accelerated, and the cloud began to flatten into a disk shape, much like pizza dough spinning in the air. At the center of this disk, where most of the mass concentrated, pressure and temperature began to rise dramatically. The material packed together so tightly that atoms started to collide with tremendous force. The core grew hotter and hotter, reaching temperatures of millions of degrees. Eventually, the conditions became so extreme that hydrogen atoms began fusing together to form helium, releasing enormous amounts of energy. This was the moment our sun ignited, transforming from a dark clump of gas into a brilliant star. The young sun was different from the stable star we see today. It was more active, more violent, with powerful stellar winds that would play a crucial role in shaping the planets to come. Meanwhile, in the disk of materials surrounding the newborn sun, the first seeds of planets were taking shape. The disk wasn't smooth but filled with countless particles of dust and ice, ranging from microscopic grains to pebbles. These particles orbited the young sun at slightly different speeds depending on their distance from the center. This difference in orbital velocity meant that particles constantly bumped into each other. Sometimes they bounced apart, but often, especially with smaller particles, they stuck together through electrostatic forces, similar to how dust clings to a television screen. Through this process of accretion, dust grains combined to form larger clumps. These clumps collided with other clumps, forming pebbles. Pebbles joined to create boulders. The process continued, slowly but relentlessly, over millions of years. The disk around our sun was becoming less uniform, with certain regions developing concentrations of material that would eventually become planets. The temperature of the disk varied greatly depending on distance from the sun close to our young star. The intense heat vaporized lighter materials like water ice and methane. Only materials with high melting points, such as metals and silicate rocks, could remain solid in the inner solar system. This is why the inner planets, including Earth, are rocky. Farther out, beyond what scientists call the frost line, temperatures were low enough for ice to remain solid. This allowed the outer planets to grow much larger, accumulating vast amounts of frozen material along with gases. As millions of years passed in the spinning disk around our young sun, the boulder-sized clumps of material continued their patient accumulation. Eventually, through countless collisions and gravitational attraction, some of these grew to sizes measured in kilometers rather than meters. Scientists call these larger bodies planetesimals, the building blocks of planets. These weren't uniform spheres like modern planets, but irregular chunks of rock and metal tumbling through space. The planetesimals that formed in Earth's region of the solar system, about 150 million kilometers from the sun, consisted primarily of silicate rocks and metallic elements like iron and nickel. Unlike the icy planetesimals forming farther out in the colder regions of the solar system, these inner system bodies were dry and rocky, shaped by the intense heat radiating from the young sun. As planetesimals grew larger, their gravitational pull increased. This created a feedback effect, a runaway process where the bigger an object became, the more effectively it could attract nearby material. The largest planetesimals began to dominate their orbital neighborhoods, sweeping up smaller bodies in their paths like cosmic vacuum cleaners. Through this process, the thousands of planetesimals that once filled the inner solar system gradually consolidated into just a handful of larger bodies. Around 4,500 million years ago, one of these growing bodies would eventually become our Earth. At this stage, Proto-Earth was far from the planet we know. It was a world under constant bombardment, with planetesimals of all sizes raining down upon its surface. Each impact released tremendous energy. When a planetesimal struck the surface, the kinetic energy of motion converted instantly into heat, like rubbing your hands together but on an unimaginable scale. These impacts didn't just add mass to the growing planet. They fundamentally shaped its internal structure. The bombardment generated so much heat that Proto-Earth's interior began to melt. This created what scientists call a magma ocean, a global layer of molten rock extending hundreds of kilometers beneath the surface. Current research using isotopic dating of meteorites suggests that this phase of Earth's growth lasted somewhere between 10 and 100 million years, though the exact timeline remains an area of active scientific inquiry. During this molten phase, something crucial occurred. The laws of physics dictated that denser materials would sink toward the center while lighter materials rose to the surface. Iron and nickel, being much denser than silicate rocks, began a gradual descent through the molten interior. This process, sometimes called the iron catastrophe, resulted in the separation of Earth into distinct layers. The heavy metals accumulated at the center, forming Earth's core. The lighter silicate rocks remained closer to the surface, eventually forming the mantle and crust. This differentiation into layers had profound consequences for Earth's future. The metallic core would eventually generate the planet's magnetic field, a shield protecting the surface from harmful solar radiation. Without this magnetic field, life as we know it would likely never have developed. The layered structure also enabled plate tectonics, the process that continually renews Earth's surface and plays a vital role in regulating climate over geological timescales. The young Earth during this period was nothing like the blue marble we see from space today. Its surface glowed red with heat from countless impacts and the molten rock below. There were no oceans, no atmosphere as we would recognize it, no continents. Just a hellish world of molten stone and metal, constantly reshaped by the violence of formation. Yet within this chaos, the seeds of our future home were being planted, layer by layer, impact by impact, as gravity and physics worked their patient alchemy. Earth's formation might have proceeded relatively peacefully from this point, gradually cooling and solidifying over millions of years. But approximately 4,500 million years ago, something catastrophic happened that would forever change our planet's destiny and give us one of the most beautiful sights in our night sky. Another planetary body, roughly the size of Mars, was following an orbit through the inner solar system. Scientists have named this vanished world Theia, after the Greek goddess who gave birth to Selene, the goddess of the moon. Based on computer simulations and analysis of lunar samples, researchers believe Theia formed either in a similar region of the solar nebula as Earth or possibly at one of the gravitationally stable points in Earth's orbit. Over time, gravitational interactions with other bodies in the forming solar system altered Theia's path. Its orbit became increasingly unstable until eventually, the inevitable occurred. Theia collided with Proto-Earth in what remains one of the most violent events in our planet's history. The impact happened at an oblique angle rather than head-on, with Theia striking Earth's surface at a velocity of several kilometers per second. The energy released by this collision staggers the imagination. In an instant, both worlds were partially vaporized. Rock that had been solid became gas. The outer layers of both planets were blasted into space, creating an expanding cloud of molten droplets and vaporized stone. Some of this material escaped the Earth-Theia system entirely, lost forever to space. But much of it remained trapped in orbit around what was left of Proto-Earth, held by gravity into a ring of debris encircling the battered planet. The collision had several crucial effects beyond simply increasing Earth's mass. First, it dramatically increased Earth's rotation rate. Before the impact, Proto-Earth probably rotated once every 5 to 6 hours. The angular momentum imparted by Thea's glancing blow set Earth spinning even faster initially, though this rotation would gradually slow over billions of years due to tidal interactions with the Moon. Second, the impact redistributed material between the two worlds, mixing their mantles while leaving their metallic cores largely intact. Perhaps most importantly for life's eventual emergence, the collision's energy was so intense that it created a global magma ocean on Earth's surface. The entire planet became molten once again, erasing all evidence of its earlier surface features. For perhaps 2 million years after the impact, Earth was enveloped in a thick atmosphere of rock vapor. As this rock vapor gradually condensed, it released enormous amounts of heat, preventing the surface from cooling quickly. The planet glowed with its own light, radiating heat into space like a dying ember. Meanwhile, the debris ring around Earth began its own transformation. Gravity works on all scales, and the countless fragments in orbit started to clump together, just as the original planetesimals had in the solar nebula. The process was remarkably fast by geological standards. Some recent simulations suggest that the Moon could have formed in a matter of hours to thousands of years after the impact, though other models propose longer timescales. The newly formed Moon was initially much closer to Earth than it is today, perhaps only 20,000 kilometers away compared to its current distance of 384,000 kilometers. It appeared enormous in the sky, many times larger than we see it now. The gravitational interaction between Earth and its new companion was intense, causing tremendous tides that flexed and heated both bodies. Over billions of years, tidal forces have gradually pushed the Moon away from Earth at a rate of about 4 centimeters per year, a process that continues even today. After the chaos of the giant impact, Earth entered a period that scientists call the Hadean Aeon, named after Hades, the Greek underworld. This name captures perfectly the hellish conditions that prevailed on our planet during this time, roughly 4,500,000,000 to 4 billion years ago. The surface remained far too hot for solid rock to form, covered instead by a global ocean of molten magma that glowed red in the darkness of space. The magma ocean wasn't uniform in depth. Current models suggest it may have extended down several hundred kilometers, perhaps as deep as 1,000 kilometers in some regions. Below this molten layer, the pressure was so immense that the rock remained solid despite the extreme temperatures, forming the beginnings of Earth's deep mantle. Convection currents churned through the magma ocean, hot material rising from below while cooler material sank, creating a constant roiling motion like a pot of boiling water scaled up to planetary dimensions. Cooling a planet the size of Earth is not a quick process. The rate at which heat could escape into space was limited by the thick atmosphere that surrounded the young planet. This atmosphere, quite different from the one we breathe today, consisted primarily of water vapor along with carbon dioxide, nitrogen, and smaller amounts of other gases. These gases had been released from the molten rock through a process called outgassing, similar to how bubbles form in boiling water as dissolved gases escape. The water vapor was particularly important in controlling Earth's cooling rate. Like a blanket trapping heat, the dense steam atmosphere acted as a powerful greenhouse, preventing rapid heat loss to space. Earth's surface temperature during this period may have hovered around 800 to 1,000 degrees Celsius. Under these conditions, water could not exist as a liquid on the surface, remaining instead as vapor in the atmosphere. As millions of years passed, the magma ocean gradually solidified from the bottom up. This happened because the melting point of silicate rocks increases with pressure. Deep in Earth's interior, the pressure was so great that despite the high temperatures, the rock reached a point where it could no longer remain molten. A solid layer began to form at the base of the magma ocean, slowly growing upward like ice forming on the surface of a pond, but in reverse. Eventually, perhaps 2 million years after the moon-forming impact, the solidification process reached Earth's surface. For the first time since the Great Collision, the planet had a solid crust. This early crust was likely quite thin and unstable, constantly being broken up and recycled back into the partially molten interior below. Imagine a surface covered with dark, basaltic rock, fractured and glowing red from the heat beneath. Once the surface solidified enough to lower the surface temperature below the boiling point of water, the thick steam atmosphere began to condense. Rain started to fall, but this was unlike any rain seen in billions of years since. The raindrops sizzled and evaporated the moment they touched the superheated rock, creating vast clouds of steam that rose back into the atmosphere only to condense and fall again. This cycle repeated countless times, each time removing a bit more heat from the surface. Gradually, over thousands or perhaps tens of thousands of years, the surface cooled enough that water could remain liquid. The rain fell and finally stayed, pooling in low areas and depressions in the new crust. The first oceans began to form. These were not the blue oceans we know today, but likely had a greenish or brownish tint due to dissolved minerals and iron compounds. The early ocean was probably quite hot, perhaps close to 100 degrees Celsius, but it was liquid water nonetheless, a crucial ingredient for life. With a solid surface and the first accumulations of liquid water, Earth entered a new phase of its development. The planet was still hostile to life as we know it, but it was no longer the hellish world of the Hadean Aeon. The formation of a stable atmosphere and ocean would prove crucial for everything that followed, including the eventual emergence of biology. Scientists distinguish between Earth's primary and secondary atmospheres. The primary atmosphere, if it ever existed, would have been composed mainly of hydrogen and helium captured directly from the solar nebula during Earth's formation. However, the young sun's intense radiation and powerful stellar winds likely stripped away any primordial atmosphere early in Earth's history. The atmosphere we need to understand is the secondary one, formed through volcanic outgassing from Earth's interior. Every time a volcano erupts on modern Earth, it releases gases from deep within the planet. The same process occurred with far greater intensity on the young Earth, as volcanic activity was much more vigorous than today. The gases released included water vapor, carbon dioxide, nitrogen, sulfur dioxide, and smaller amounts of other compounds. Importantly, these volcanic emissions contained virtually no free oxygen, the gas that makes up 21% of our current atmosphere. The composition of Earth's early atmosphere remained very different from today's for billions of years. Carbon dioxide was far more abundant, perhaps accounting for most of the atmosphere apart from nitrogen and water vapor. This thick carbon dioxide atmosphere created a strong greenhouse effect, keeping surface temperatures warm even as the sun was about 30% dimmer than it is now. Scientists call this puzzle of how early Earth remained warm despite a fainter sun the faint young sun paradox, and the greenhouse effect from carbon dioxide and other gases provides the most likely solution. The source of Earth's water has been a subject of considerable scientific debate. For many years, researchers believed that water arrived primarily from comets, those icy visitors from the outer solar system. However, recent studies comparing the isotopic composition of water in comets, asteroids, and Earth's oceans have revealed a more nuanced picture. The deuterium to hydrogen ratio, a sort of fingerprint that varies between different sources of water in the solar system, suggests that Earth's water came from multiple sources. Current evidence points to a combination of water delivered by impacts from water-rich asteroids from the outer regions of the asteroid belt and water that was present in the materials that originally accreted to form Earth. Some water may have existed in hydrated minerals within the planetesimals that built our planet. When these planetesimals were heated during Earth's formation, the water would have been released and eventually made its way to the surface through volcanic activity. By approximately 4 billion years ago, based on evidence from ancient zircon crystals found in Western Australia, Earth had both a solid crust and liquid water oceans. These zircon crystals, some of the oldest materials ever found on Earth, formed in the presence of water, providing direct evidence that oceans existed remarkably early in our planet's history. This finding surprised many scientists, who had expected that Earth's surface took longer to cool sufficiently for liquid water to be stable. The early oceans were probably quite acidic due to the large amounts of carbon dioxide dissolved from the atmosphere. As rainwater fell through the carbon dioxide-rich air, it formed carbonic acid, similar to carbonated water but much more concentrated. This acidic water was highly reactive, rapidly weathering rocks on the young continents. The weathering process released various elements into the ocean, including sodium, calcium, and magnesium, beginning the process of making seawater salty. Interestingly, evidence suggests that the ocean has maintained roughly similar salinity levels throughout most of Earth's history, despite the constant input of dissolved materials from weathering. While the early Earth had a solid crust within a few 100 million years of its formation, this crust was quite different from the continents we stand on today. The distinction between oceanic and continental crust represents one of the fundamental features of our planet, and understanding how continents formed tells us much about Earth's geological evolution. Oceanic crust, the type that underlies ocean basins, forms continuously even today at mid-ocean ridges. Here, molten rock from the mantle rises up and solidifies, creating new seafloor. This oceanic crust is relatively thin, averaging about 7 kilometers in thickness, and is composed primarily of basalt, a dark, dense volcanic rock. More importantly, oceanic crust is constantly recycled. As tectonic plates move, old oceanic crust is pushed back into the mantle at subduction zones, where it melts and is eventually recycled. This means that virtually no oceanic crust on Earth today is older than 200 million years, a mere blink in geological time. Continental crust is fundamentally different. It is much thicker, averaging 30 to 50 kilometers, and is composed of less dense rocks, primarily granite and related rocks rich in silica. Most crucially, continental crust is buoyant compared to oceanic crust. Like foam floating on water, continental crust is too light to be pulled down into the mantle by subduction. This means that once continental crust forms, it tends to remain at the surface, accumulating and amalgamating over billions of years. The oldest known continental rocks on Earth are the Acasta gneisses in northwestern Canada, dated to about 4 billion years ago. However, individual mineral grains called zircons found in Western Australia are even older, with some dating back to 4 billion years. These ancient zircons crystallized from molten rock in the presence of water, indicating that not only did continental crust exist very early in Earth's history, but so did liquid water oceans. The question of how continental crust first formed remains an area of active research, but scientists have developed several complementary theories. In the very early Earth, when the planet's interior was much hotter than today, volcanic activity was far more intense. Some researchers propose that mantle plumes, massive upwellings of hot rock from deep within the planet, rose to the surface and melted partially. This partial melting is key because it naturally separates lighter, silica-rich minerals from denser ones. The lighter material, being less dense, would rise to form protocontinents while the denser material sank back into the mantle. Another important process in creating continental crust involves the recycling of oceanic crust at subduction zones. When oceanic crust is pushed down into the mantle, The increasing pressure and temperature cause it to release water and other volatiles. These fluids rise into the overlying mantle wedge, lowering its melting point and causing partial melting. The resulting magma is less dense and more silica-rich than the original oceanic crust. This magma rises toward the surface, sometimes erupting from volcanoes, sometimes cooling underground to form granite. Over time, this process can build up significant volumes of continental crust. Evidence suggests that the rate of continental crust formation was not constant throughout Earth's history. There appears to have been a peak in crustal growth between 3 and 2.5 billion years ago, during a period of dramatic geological change. Before about 3 billion years ago, Earth's continental crust may have been predominantly mafic, meaning it was denser and darker than modern continental crust. After this transition period, continental crust became more felsic, richer in silica and lighter in color and density, resembling the granite-dominated continents we know today. Earth is unique among the planets in our solar system in possessing active plate tectonics. This geological process, where large segments of the crust move slowly over the underlying mantle, profoundly shapes our planet's surface and plays a crucial role in regulating climate and supporting life. But plate tectonics didn't begin immediately when Earth formed. Understanding when and how this process started remains one of the most debated questions in geology. Plate tectonics requires specific conditions to operate. The crust must be rigid enough to form distinct plates, yet the underlying mantle must be able to flow slowly over geological timescales. There must be dense oceanic crust that can sink into the mantle, initiating subduction. The planet must also be losing enough internal heat that convection currents in the mantle are vigorous enough to move the plates. In the very early Earth, conditions were quite different from today, and the style of tectonics may have been different as well. One challenge in determining when plate tectonics began is that the process erases much of its own evidence. At subduction zones, old oceanic crust is pulled down into the mantle where it melts and is recycled. This means that direct evidence of ancient seafloor spreading is extremely rare. Similarly, the constant creation and destruction of crust at plate boundaries means that the oldest continental rocks have often been deformed, metamorphosed, and altered beyond easy interpretation. Despite these challenges, geologists have assembled various lines of evidence to constrain when plate tectonics might have begun operating in a manner similar to today. One approach involves looking for specific rock types and geological structures that form only in plate tectonic settings. For example, rocks called ophiolites, which represent slices of oceanic crust and upper mantle that have been thrust up onto continents, provide direct evidence of ancient ocean basins. The oldest confirmed ophiolites date back to about 3 billion years ago. Another telltale sign of plate tectonics is paired metamorphic belts. When an oceanic plate subducts beneath a continent, two distinct zones of metamorphism develop. Near the subduction zone, rocks are subjected to high pressure but relatively low temperature, creating one type of metamorphic rock. Farther inland, above where the subducting plate releases fluids and causes melting, rocks experience high-temperature metamorphism. These paired belts of different metamorphic rocks are characteristic of subduction zones and have been identified in rocks dating back about 700 million years with certainty, though some researchers claim to have found older examples. The chemistry of ancient rocks also provides clues. Certain patterns in trace elements and isotopes are characteristic of rocks formed in subduction zone settings. Analysis of rocks between 3 billion, 800 million, and 2 billion, 700 million years ago shows that some have subduction-related chemical signatures while others formed in non-subduction settings. This coexistence of different magma types suggests that while some form of plate recycling may have been occurring, it may not have been operating globally as it does today. Many researchers now favor the view that plate tectonics began operating in a modern style sometime between 3 billion and 2.5 billion years ago. Before this time, Earth's interior was hotter, and the crust may have been too weak to form rigid plates. Instead, the planet may have operated under a different tectonic regime, perhaps one where the crust behaved more like a thick, stagnant lid periodically broken up by rising mantle plumes, or where smaller, shorter-lived episodes of subduction occurred without the continuous, planet-wide system we see today. The transition to plate tectonics had profound implications for Earth's evolution. It established a mechanism for recycling carbon dioxide between the surface and interior, helping to regulate climate over billion-year timescales. It created diverse geological environments where different minerals and rock types could form. And it may have been crucial for the development and evolution of life. By 2.5 billion years ago, the major pieces of Earth's geological puzzle were falling into place. The planet had cooled sufficiently that a stable crust could persist. Oceans covered much of the surface, though they were arranged quite differently than today. Plate tectonics was operating, moving fragments of continental crust around the globe and creating a cycle of supercontinent formation and breakup. The stage was set for the Earth we know. The continents that existed in Earth's early history bear little resemblance to the familiar shapes of modern continents. Through the constant motion of plate tectonics, continents collide, merge, and split apart over hundreds of millions of years. Scientists have identified several ancient supercontinents, vast land masses where most or all of Earth's continental crust was assembled into a single massive continent. The oldest proposed supercontinent, called Valbara, may have existed around 3 billion years ago, though evidence for it remains fragmentary. Better documented is Kinnerland, which appears to have formed around 2,700 million years ago and broken apart about 2,500 million years ago. After Kinnerland's breakup, the continental fragments eventually reassembled into another supercontinent called Columbia or Nuna, which existed from about 1,800 million to 1,500 million years ago. This pattern of assembly and dispersal would continue throughout Earth's history, with the most recent supercontinent, Pangaea, beginning to break apart just 200 million years ago, ultimately forming the familiar arrangement of continents we see today. The formation and breakup of supercontinents has significant effects on Earth's climate and environment. When continents cluster together into a supercontinent, there is less coastline relative to land area, which affects ocean circulation patterns. The interior of a supercontinent tends to experience extreme temperature variations and low rainfall, creating vast deserts. When a supercontinent breaks apart, rifting creates new ocean basins, and increased volcanic activity at the spreading centers can affect atmospheric composition. As Earth's surface evolved, so did its atmosphere. For the first 2 billion years of Earth's history, the atmosphere contained little to no free oxygen. This changed dramatically around 2,400 million years ago in what scientists call the Great Oxidation Event. Photosynthetic organisms, primarily cyanobacteria, had been producing oxygen as a waste product for hundreds of millions of years. Initially, this oxygen reacted with dissolved iron in the oceans and reduced minerals on land, effectively being scrubbed from the atmosphere. Eventually, these oxygen sinks became saturated. The iron in the oceans had been oxidized and precipitated out, forming distinctive bands of iron-rich rock called banded iron formations. With nowhere else to go, oxygen began accumulating in the atmosphere, fundamentally changing Earth's chemistry and paving the way for the evolution of more complex life forms that could harness this reactive gas for more efficient metabolism. From our vantage point 4.5 billion years later, we can trace Earth's remarkable journey from a disk of dust and gas to the dynamic, life-supporting planet we inhabit. Every aspect of our world, from the solid ground beneath our feet to the air we breathe, is the product of billions of years of geological processes. The water in our oceans has been recycled through the rock cycle countless times. The continents we live on are fragments of ancient supercontinents, reassembled in new configurations. Even the atoms in our bodies were forged in stars that died long before our solar system formed. And on that note, our journey through Earth's formation comes to a close. Thank you for joining me on this voyage through deep time. I hope you found it both enlightening and calming. The distance to Mars varies as both planets orbit the Sun, ranging from 55 million kilometers at their closest approach to over 400 million kilometers when they are on opposite sides of the solar system. Mission planners choose a launch window when the planets are favorably aligned, allowing spacecraft to follow an efficient curved path called a Hohmann transfer orbit. Think of this trajectory like a bridge between two moving cars on a circular racetrack. You can't simply aim straight at where Mars is now, because by the time you arrive, Mars will have moved. The journey typically takes between 6 and 9 months. As our spacecraft climbs away from Earth, the blue marble of our home world gradually shrinks against the blackness. Once we've escaped Earth's gravitational embrace and settled into our transfer orbit, the engines shut down. From this point forward, we coast through space, following the natural curves of gravity around the Sun. The silence is profound. In the vacuum of space, there's no air to carry sound waves. Through the windows, stars shine without twinkling, their light undisturbed by atmospheric turbulence. Inside our spacecraft, daily routines help maintain a sense of normalcy during the months-long voyage. In microgravity, there is no up or down. Astronauts float freely through the cabin, pushing off walls to glide from one module to another. This weightlessness occurs because the spacecraft and everything inside it are falling toward the Sun together, following the curved path of their orbit. It's similar to the feeling in an elevator that suddenly begins descending, except the sensation never ends. Your inner ear, which normally senses gravity's pull, becomes confused, often causing space sickness during the first few days. Sleeping in space requires strapping into a sleeping bag attached to a wall. The spacecraft maintains an artificial day and night cycle using timed lighting, helping regulate circadian rhythms that evolved over millions of years under Earth's Sunday meals consist of carefully preserved food, with fresh fruits and vegetables running out quickly, giving way to freeze-dried packages that require adding water. Exercise is crucial during the journey. Without gravity's constant pull, muscles and bones begin weakening. Astronauts spend several hours each day using resistance bands and modified equipment to minimize deterioration. The psychological challenges deserve consideration. You're confined with a small crew in a tiny spacecraft, millions of kilometers from home. Earth appears as merely a bright star through the window, sometimes lost in the sun's glare. Communication delays grow longer as the distance increases. Messages take between 3 and 22 minutes to travel one way, depending on where Mars and Earth are in their orbits, making real-time conversations impossible. The region between Earth and Mars might seem empty, but it contains more than pure vacuum. Solar radiation streams past our spacecraft constantly. The Sun produces this radiation through nuclear fusion in its core, where hydrogen atoms combine under immense pressure and temperature to form helium, releasing tremendous energy. Charged particles also flow from the sun in what scientists call the solar wind. This supersonic stream of protons, electrons, and other ions rushes through the solar system at speeds around 400 kilometers per second. Cosmic rays pose another concern. These high-energy particles originate from outside our solar system, created by supernova explosions and other violent astronomical events. When cosmic rays strike atoms, they can damage biological cells, potentially causing cancer or other health problems. Earth's magnetic field and thick atmosphere protect us from most cosmic radiation, but spacecraft offer only minimal shielding. Between the planets drifts dust, remnants from the formation of our solar system 4.5 billion years ago. The spacecraft moves through this environment at approximately 25 kilometers per second relative to the Sun, though inside it feels perfectly still. As the weeks pass and we draw nearer to our destination, Mars grows from a reddish star into a visible disk. Through telescopes aboard our spacecraft, surface features become discernible. The planet's characteristic rust color comes from iron oxide, essentially rust, covering much of the Martian terrain. This iron oxidized long ago when Mars possessed a thicker atmosphere and liquid water on its surface. Mars is smaller than Earth, with a diameter of roughly 6,790 kilometers compared to Earth's 12,742 kilometers. Think of Earth as a basketball, and Mars would be roughly the size of a softball. Despite this smaller size, Mars has nearly the same amount of land surface area as Earth because it lacks oceans. All of Earth's continents combined would fit comfortably on Mars with room to spare. The planet rotates once every 24 hours, 37 minutes, and 22 seconds, remarkably similar to Earth's day. This near match is coincidental, as planetary rotation periods vary widely throughout the solar system. Mars also has seasons, caused by its tilted axis just like Earth's seasons. However, Martian seasons last almost twice as long because Mars takes 687 Earth days to complete one orbit around the Sun. Two small moons orbit Mars. Phobos, the larger inner moon, measures only about 22 kilometers across at its widest point and orbits so close to Mars that it circles the planet 3 times each Martian day. Deimos, the smaller outer moon, spans roughly 12 kilometers and takes 30 hours to orbit. Both moons are probably captured asteroids, their irregular shapes suggesting they formed elsewhere and were later snared by Martian gravity. Through our instruments, we can measure Mars's thin atmosphere, composed of 95% carbon dioxide with traces of nitrogen, argon, and other gases. The atmospheric pressure at the Martian surface averages only 0.6% of Earth's sea level pressure. This is equivalent to the pressure you'd experience roughly 35 kilometers above Earth's surface, 3 times higher than commercial aircraft cruise. A human on Mars without a pressure suit would face rapid decompression, similar to suddenly appearing in the vacuum of space. Temperature readings reveal a cold world. The average surface temperature hovers around -63 degrees Celsius, though it can reach a relatively balmy 20 degrees Celsius at the equator during summer afternoons before plunging to -125 degrees Celsius at the poles during winter nights. These extreme temperature swings occur partly because the thin atmosphere retains little heat and partly because Mars orbits farther from the Sun than Earth does, receiving only 43% as much solar energy per square meter. As we continue our approach, it's worth reflecting on what Mars once was. Billions of years ago, the red planet told a different story. Evidence gathered by orbital probes and surface rovers reveals that ancient Mars possessed abundant liquid water, flowing in rivers, pooling in lakes, and possibly filling a northern ocean. The presence of certain clay minerals that form only in water, along with rounded pebbles smoothed by ancient streams, points to a warmer, wetter past. Scientists believe that early Mars had a much thicker atmosphere, perhaps dense enough to support liquid water at the surface despite the planet's greater distance from the Sun. This ancient atmosphere may have contained greenhouse gases that trapped heat, similar to the way Venus's thick carbon dioxide atmosphere creates a runaway greenhouse effect today, though Mars's early greenhouse was less extreme and more hospitable. Something changed. Over hundreds of millions of years, Mars lost most of its atmosphere. The leading theory involves the solar wind we discussed earlier. Mars either never had or lost its global magnetic field, which on Earth extends thousands of kilometers into space, deflecting charged particles from the Sun. Without this protective shield, the solar wind struck Mars's upper atmosphere directly, gradually stripping away gases and carrying them off into space. Imagine a sandstorm slowly eroding a sand castle. Each gust removes a few grains, and given enough time, the entire structure disappears. The solar wind acted similarly on Mars's atmosphere, though operating over geological timescales. As the atmosphere thinned, surface pressure dropped, and temperatures fell. Liquid water became unstable, either freezing or evaporating. The planet gradually transformed into the cold desert we see today. Yet water didn't completely vanish. Significant quantities remained frozen in the polar ice caps, which contain both water ice and frozen carbon dioxide. Additional water ice lies buried under the surface at higher latitudes, detected by orbiting instruments that measure hydrogen concentrations in the soil. Some estimates suggest that if all this buried ice melted, it would create a global ocean several meters deep across the entire planet. Seasonal changes still involve water, though in frozen form. During Martian winter, carbon dioxide from the atmosphere freezes onto the polar caps, and during summer, it sublimes directly from ice to gas, bypassing the liquid phase. Water ice remains frozen year-round at the poles, but small amounts of frost can appear at mid-latitudes during cold seasons. Occasionally, dark streaks appear on sun-facing slopes during warm periods, possibly indicating briny water flows, though this interpretation remains debated among planetary scientists. Understanding Mars's watery past matters for astrobiology, the study of life beyond Earth. Wherever liquid water exists on Earth, even in extreme environments, we find organisms. Did life ever arise on ancient Mars when conditions were more favorable? If so, might dormant microbes still survive in protected subsurface environments where ice occasionally melts? These questions drive much of current Mars exploration and add philosophical weight to our journey. After months of travel, Mars now fills our windows. The moment for orbital insertion approaches, one of the most critical phases of the entire mission. Our spacecraft has been coasting, but now we must slow down relative to Mars to be captured by its gravity. If we maintain our current velocity, we'll simply swing past the planet and continue into solar orbit, missing our destination entirely. The spacecraft rotates, pointing its main engine toward our direction of travel. Retrothrusters fire, and we feel weight again for the first time in months as deceleration pushes us against our restraints. This burn must be executed with precision. Too little deceleration and our orbit will be too elliptical, possibly sending us back toward the inner solar system. Too much and we might descend too quickly, risking collision with the planet or entry into the upper atmosphere before we're ready. Mission Control on Earth calculated this burn months ago, but the vast distance means they can't adjust anything in real time. By the time our signal reaches Earth, traveling at the speed of light, the maneuver will already be finished. We're on our own, trusting in the calculations and the spacecraft's automated systems. The burn lasts several minutes, consuming much of our remaining fuel. Then silence returns as the engines shut down. We've successfully entered Mars' orbit. Checking our instruments, we confirm that we're following an elliptical path around the planet, closest approach at a few hundred kilometers altitude, farthest point extending several thousand kilometers out. Over the coming days or weeks, depending on mission plans, we might adjust this orbit, performing smaller burns to circularize our path or change our inclination relative to Mars's equator. From orbit, the planet reveals its wonders. The immense canyon system of Valles Marineris stretches across our view, a scar in the Martian surface extending over 4,000 kilometers long, up to 7 kilometers deep, and 600 kilometers wide at its broadest point. To put this in perspective, if Valles Marineris were on Earth, it would stretch from New York to Los Angeles. The Grand Canyon would fit comfortably inside one of its smaller side channels. In another region, the Tharsis volcanic plateau rises into view, home to the solar system's tallest mountain. Olympus Mons towers 21 kilometers above the surrounding plains, about 2.5 times the height of Mount Everest above sea level. The volcano's base spans roughly 600 kilometers, similar to the size of Arizona. It formed over billions of years through countless eruptions, gradually building layer upon layer of cooled lava. The low Martian gravity allowed the structure to grow far taller than possible on Earth, where higher gravity would cause such a massive mountain to collapse under its own weight. The northern and southern hemispheres of Mars show striking differences. The northern plains are smooth and low, possibly the floor of an ancient ocean. The southern highlands are rugged and cratered, scarred by billions of years of meteorite impacts. This hemispheric dichotomy remains somewhat mysterious, though theories suggest a giant impact early in Mars's history might have blasted away much of the northern crust. As we orbit the red planet, studying it from above, we can observe the dynamic processes still shaping Mars today. Dust storms, sometimes growing to engulf the entire planet, demonstrate that Mars remains geologically and meteorologically active, though in ways quite different from Earth. These global dust events can last for months, driven by seasonal heating patterns and the planet's elliptical orbit. When Mars passes through its closest approach to the Sun, the southern hemisphere experiences summer. Increased solar heating stirs the thin atmosphere, lifting fine dust particles high into the air. Under the right conditions, local storms merge and intensify, eventually covering the entire planet in a reddish haze. From orbit, surface features disappear beneath the dust, and instruments detect plummeting temperatures as the suspended particles block sunlight from reaching the ground. The dust itself is incredibly fine, comparable to cigarette smoke or talcum powder. It settles slowly in the low gravity and thin air, taking weeks to clear after a storm subsides. This fine dust poses challenges for any surface operations, clogging mechanisms, coating solar panels, and potentially causing health problems if inhaled. Static electricity makes the dust cling to everything it touches, another consequence of the dry Martian environment. Frozen carbon dioxide creates seasonal phenomena at the poles. During winter, temperatures drop low enough that carbon dioxide gas from the atmosphere freezes directly onto the polar cap, growing it substantially. This seasonal cap can extend to latitudes as low as 50 degrees, roughly equivalent to Newfoundland or southern England on Earth. When spring returns, the frozen carbon dioxide sublimes, releasing gas back into the atmosphere. Sometimes this sublimation occurs beneath translucent ice layers, building up pressure until it explosively vents, creating geyser-like eruptions that blast dark dust across the surrounding terrain. The permanent polar caps beneath these seasonal layers contain water ice mixed with dust. The northern cap in particular is largely water ice, approximately 1,000 kilometers across and up to 2 kilometers thick in places. If completely melted, this ice cap alone would provide enough water to cover Mars and a global ocean roughly 10 meters deep, though the thin atmosphere would cause much of it to evaporate into space. Satellites orbiting Mars have detected methane in the atmosphere, appearing and disappearing in patterns that scientists are still trying to explain. On Earth, most atmospheric methane comes from biological sources, though geological processes can also produce it. The Martian methane might originate from microbial life, from chemical reactions between water and rock deep underground, or from decomposing organic material deposited by ancient meteorites. Each possibility has profound implications for understanding Mars. Temperature inversions in the Martian atmosphere create unusual weather patterns. Because the air is so thin, the ground cools rapidly after sunset, often becoming colder than the air above it. This inverted temperature profile suppresses vertical mixing, trapping dust and other particles near the surface. Astronauts standing on Mars during evening hours would see the horizon fade into a murky haze, quite different from Earth's clear twilight skies. Mars's geological history spans 4.5 billion years, telling a story written in stone and ice across its surface. Unlike Earth, where plate tectonics constantly recycle the crust, Mars appears to lack this process. Its surface preserves ancient features that would have been destroyed long ago on our dynamic home world. This geological stillness makes Mars a museum of planetary evolution, offering insights into processes that shaped the early solar system. The planet's surface divides into distinct regions, each telling part of the story. The southern islands are heavily cratered, scarred by billions of years of meteorite bombardment. These impact craters range from tiny pits a few meters across to massive basins hundreds of kilometers in diameter. The crater density suggests the southern highlands are ancient, dating back to a period roughly 4 billion years ago when the inner solar system experienced intense bombardment. Large asteroids and comets frequently struck the young planets during this violent epoch. In striking contrast, the northern lowlands show far fewer craters, indicating a younger surface age. These smooth plains lie several kilometers lower in elevation than the southern highlands. The boundary between these two regions, called the crustal dichotomy, remains one of Mars's most intriguing mysteries. Some scientists propose that a massive impact early in Martian history blasted away much of the northern crust. Others suggest internal processes like mantle convection created the difference. Whatever the cause, this hemispheric division profoundly influenced Mars's subsequent evolution. The Tharsis Rise dominates one hemisphere, a vast volcanic plateau roughly the size of North America. This region bulges upward from the surrounding terrain, elevated by volcanic activity that began billions of years ago and may have continued until relatively recently in geological terms. The weight of Tharsis actually warped Mars's shape, creating stresses in the crust that opened the Great Canyon system of Valles Marineris along its eastern flank. Think of Tharsis as a heavy weight placed on a soft rubber ball, creating bulges and cracks in the surface. Olympus Mons rises from the Tharsis region, the largest volcano in the solar system. This shield volcano built up gradually through countless eruptions over perhaps hundreds of millions of years. Each eruption added another thin layer of lava, slowly constructing the immense edifice we see today. The caldera at its summit, where magma once welled up from below, measures 85 kilometers across and plunges nearly 3 kilometers deep. 6 nested calderas overlap at the peak, each representing a different episode of collapse as magma chambers emptied beneath the surface. Shield volcanoes on Earth, like those in Hawaii, provide useful comparisons. They form from fluid lava that flows long distances before solidifying, creating gentle slopes rather than the steep cones associated with explosive volcanoes. Olympus Mons displays this same shield profile, with slopes averaging only about 5 degrees. You could walk up its flanks without technical climbing equipment, though the hike would take weeks given the mountain's enormous size. The summit tower is so high that it extends above much of Mars's thin atmosphere. The canyon system of Valles Marineris stretches 1/5 of the way around the planet's equator. Unlike Earth's Grand Canyon, which water carved over millions of years, Valles Marineris formed primarily through geological faulting and collapse. As the Tharsis Bulge rose, it stretched the surrounding crust like pulling apart a piece of taffy. The crust fractured, and portions of the surface dropped between parallel faults, creating the immense troughs we see today. Later, landslides, erosion, and possibly water flow modified the canyon walls, but the fundamental structure resulted from tectonic forces. Looking at these geological features from orbit, we see a planet that was once geologically active, its interior hot enough to drive volcanic eruptions and crustal deformation. Today, Mars appears largely dormant. No active volcanoes have been confirmed, though some scientists argue that Olympus Mons might have erupted as recently as a few million years ago, which is quite recent in geological terms. Marsquakes detected by landers suggest the planet's interior retains some heat and activity, but nothing compared to Earth's vigorous geology. The rocks themselves tell stories too. Spacecraft orbiting Mars use spectrometers to identify minerals on the surface by analyzing reflected sunlight. These instruments have detected olivine, a green mineral that weathers quickly in water. Its presence suggests those areas have remained dry for billions of years. Other regions show clays that form only in the presence of liquid water, indicating past wet conditions. Sulfate minerals, which form in acidic water, appear in younger deposits, hinting that Mars's ancient oceans, if they existed, may have become acidic before finally evaporating. Despite decades of exploration with orbiters, landers, and rovers, Mars still guards many secrets. Each answered question seems to raise new ones, deepening our fascination with this neighboring world. Some mysteries concern Mars's past, while others involve ongoing processes we're only beginning to understand. These unknowns drive continued exploration and scientific investigation. One enduring puzzle involves methane in the Martian atmosphere. Methane molecules should break down relatively quickly under ultraviolet radiation from the sun, disappearing within a few hundred years. Yet spacecraft have detected methane in Mars's atmosphere, sometimes in concentrations that vary seasonally or geographically. Something must be replenishing this methane, but what? On Earth, most atmospheric methane comes from living organisms, though geological sources also exist. The Martian methane could indicate microbial life, perhaps dwelling in subsurface environments. Alternatively, chemical reactions between water and certain minerals deep underground might produce methane that eventually seeps to the surface. The seasonal dark streaks called recurring slope lineae present another mystery. These narrow features appear on sun-facing slopes during warm seasons, gradually extending downhill before fading when temperatures drop. When first discovered, scientists proposed these streaks might be caused by briny water flowing on the surface. Salts dissolved in the water would lower its freezing point, allowing liquid to exist temporarily despite the cold temperatures and low pressure. However, later studies suggested the streaks might form through dry processes involving sand or dust flows. The debate continues, with important implications for both the potential habitability of modern Mars and planetary protection protocols. Mars's lost magnetic field raises questions about the planet's interior structure and thermal evolution. Earth maintains its magnetic field through a geodynamo, where convection in the liquid outer core generates electrical currents that produce magnetic fields. Mars likely had a similar dynamo early in its history, but it shut down, perhaps 3 to 4 billion years ago. Why did Mars's core stop generating a magnetic field? Did the core solidify completely, or does it retain a liquid outer region that simply stopped convecting? Some researchers suggest a massive impact might have disrupted the core's convection patterns, while others propose the smaller planet simply cooled more rapidly than Earth. The fate of Mars's ancient atmosphere remains incompletely understood. We know the solar wind gradually stripped away much of the atmosphere after the magnetic field disappeared, but the exact timeline and mechanisms need clarification. Did the atmosphere disappear steadily over billions of years, or did catastrophic events accelerate the loss? Large impacts might have blasted portions of the atmosphere directly into space. Intense solar storms could have temporarily supercharged the stripping process. Understanding how Mars lost its atmosphere helps us appreciate Earth's magnetic shield and informs our search for habitable planets around other stars. Below Mars's surface might lie significant quantities of liquid water. While surface conditions prevent liquid water from existing stably, pressure increases with depth, and geothermal heat from the planet's interior could maintain temperatures above freezing in subsurface regions. Some scientists have proposed that aquifers of briny water, protected from the harsh surface environment, might exist kilometers below the ground. These hypothetical reservoirs would be prime targets in the search for Martian life, as liquid water is essential for all known biology. However, detecting subsurface water remains technically challenging. The possibility of past or present life on Mars drives much of our interest in these mysteries. If life arose independently on Mars, it would suggest that life emerges readily wherever conditions permit, implying a universe potentially teeming with biology. Conversely, if we find Mars has always been sterile despite once having favorable conditions, it might indicate that life's origin is improbable, making Earth's biosphere all the more precious. Some scientists have even suggested that life might have originated on Mars and traveled to Earth aboard meteorites, a hypothesis called panspermia. Mars cooled more quickly than Earth after formation, so it might have developed habitable surface conditions first. Evidence of past life, if it exists, might be subtle. We're not looking for fossils of large organisms, but rather microscopic traces like chemical signatures, particular mineral formations, or cellular structures preserved in ancient rocks. Rovers have found organic molecules, carbon-containing compounds that could be biological in origin or could have formed through non-biological chemistry. Distinguishing between these possibilities requires careful analysis. Future missions plan to collect samples and return them to Earth, where sophisticated laboratory equipment can examine them in unprecedented detail. Another ongoing question concerns Mars's climate cycles. The planet's axial tilt, called obliquity, varies much more dramatically than Earth's over long timescales. This happens because Mars lacks a large moon to stabilize its rotation axis. Earth's moon acts like a gyroscope, keeping our axial tilt relatively constant. Mars's obliquity can swing from near 0 degrees to perhaps 60 degrees or more over periods of hundreds of thousands to millions of years. These dramatic changes would cause wild climate swings, potentially redistributing ice between the poles and equatorial regions, alternately burying and exposing surface features under layers of ice and dust. Orbiting Mars, gazing down at its rust-colored deserts and polar ice, we can reflect on what this journey represents. Humanity evolved on Earth, shaped by its gravity, atmosphere, and magnetic field. Every organism that has ever existed, every civilization that has risen and fallen, every thought ever contemplated, occurred on that distant blue dot now hundreds of millions of kilometers away. Coming to Mars, even in imagination, shifts our perspective. The engineering required for such a voyage pushes human capability to its limits. Spacecraft must function flawlessly for months in the harsh radiation environment of interplanetary space. Life support systems must recycle air and water with extraordinary efficiency. Navigation demands precision, threading a path through space to intercept a moving target across vast distances. Every component, every line of code, every calculation must work correctly because there's no roadside assistance in the space between worlds. Yet the technical challenges pale beside the philosophical implications. Mars stands as the next step beyond Earth, the most accessible world where humans might someday establish a permanent presence. While the Moon offers valuable experience and resources only 3 days away, Mars presents the possibility of eventual self-sufficiency. Its day length matches our circadian rhythms. Its soil contains minerals that could support agriculture in greenhouses. Water ice could provide drinking water, oxygen to breathe, and hydrogen fuel for rockets. The raw materials for a civilization exist on Mars, waiting for human ingenuity to unlock them. The question isn't whether humans will go to Mars, but when and how. Multiple space agencies and private companies are developing the technology required. Plans range from brief exploratory missions to ambitious schemes for permanent settlements. Some proposals involve sending cargo ahead, using robotic systems to extract water from ice and produce fuel and oxygen before astronauts arrive. Others envision growing communities under domes or in underground habitats, protected from radiation and the harsh surface conditions. These future Martians will face challenges unlike anything encountered on Earth. They'll need to be largely self-sufficient, unable to rely on quick resupply missions when something breaks. The psychological strain of knowing that Earth is months away, that no rescue is possible if something goes catastrophically wrong, will test human resilience. Yet history shows that humans adapt to extraordinary circumstances when necessary, finding ways to thrive in environments from Arctic ice to deep deserts to the depths of the ocean. Perhaps most importantly, going to Mars forces us to think about Earth differently. From interplanetary space, our home world appears fragile, a delicate blue sphere wrapped in a thin layer of life-sustaining atmosphere. The vast emptiness between planets emphasizes how rare and precious Earth is, how carefully we should steward our only home. Even as we reach toward Mars and beyond, Earth remains our origin, the planet that gave rise to consciousness capable of wondering about the cosmos. As our orbit carries us around Mars once more, passing over ancient riverbeds and towering volcanoes, we can appreciate both how far we've come and how much farther we have to go. The journey to Mars, whether undertaken physically or in imagination, reminds us that we're part of something larger than ourselves, inhabitants of a universe filled with wonders waiting to be discovered. And on that note, our peaceful journey to Mars comes to an end. We've traveled together across millions of kilometers, explored the challenges of interplanetary spaceflight, and contemplated what this neighboring world might reveal about our place in the cosmos. Thank you for joining me on this voyage through the solar system. I hope you found it relaxing and perhaps learned something new about the red planet that has fascinated humanity throughout history. Jupiter stands as a monument to scale in our solar system. To truly grasp its size, imagine this: you could fit 1,321 Earths inside Jupiter's volume. If Earth were a marble, Jupiter would be a basketball sitting beside it. This gas giant measures approximately 89,000 miles across at its equator, more than 11 times wider than our home planet. When you look up at the night sky and spot Jupiter's steady, bright glow, you're seeing a world so massive that it contains more than twice the mass of all other planets in our solar system combined. The giant formed roughly 4.5 billion years ago in the early days of our solar system. Current models suggest that Jupiter began as a rocky core about 10 to 20 times the mass of Earth. This core acted like a cosmic vacuum cleaner, pulling in vast quantities of hydrogen and helium gas from the surrounding nebula. The process happened quickly in astronomical terms, perhaps within just a few million years. Once Jupiter reached a certain mass, its gravity became so powerful that it could capture gas directly from the solar nebula, growing rapidly into the colossus we see today. Jupiter's composition mirrors the early solar system itself. Approximately 75% of the planet consists of hydrogen, while helium makes up most of the remaining 25%. Trace amounts of methane, ammonia, water vapor, and other compounds add color and character to the giant's appearance. Unlike Earth, which has a solid surface you could theoretically stand upon, Jupiter is a world without a true surface. Instead, it's an enormous sphere of gas that gradually becomes denser and hotter as you descend toward its core. The planet completes one rotation in just under 10 hours, making it the fastest spinning planet in our solar system. This rapid rotation creates a powerful centrifugal force that causes Jupiter to bulge noticeably at its equator. If you could measure carefully, you'd find that the distance across Jupiter's equator exceeds the distance between its poles by about 6,000 miles. This oblate shape is visible even through modest backyard telescopes, adding to the planet's distinctive appearance in the night sky. Perhaps no feature of Jupiter captures the imagination quite like the Great Red Spot. This enormous storm has been raging for at least 190 years, and possibly much longer. When astronomers first began making detailed observations of Jupiter in the 1800s, the spot was already prominent. Some historical observations from the 1600s may have documented the same storm, suggesting it could be 350 years old or more. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in Jupiter's southern hemisphere. To put its size in perspective, imagine a storm system large enough to swallow 2 or 3 Earths whole. At its widest point in the late 1800s, the spot measured roughly 25,000 miles across. In recent decades, astronomers have watched it gradually shrink. Today it spans about 10,000 miles, still impressively large but noticeably smaller than in historical observations. The spot's distinctive reddish color has puzzled scientists for generations. The leading explanation involves complex chemical reactions occurring high in Jupiter's atmosphere. Sunlight and cosmic radiation may trigger reactions between ammonia, methane, and other compounds, producing red and brown organic molecules called tholins. These colorful compounds become concentrated in the high-pressure system of the Great Red Spot, giving it that characteristic rust-colored appearance. The exact chemistry remains an area of ongoing research, with scientists still working to fully understand the processes involved. The storm itself represents a remarkable example of atmospheric stability. Unlike hurricanes on Earth, which draw energy from warm ocean waters and typically last days or weeks, Jupiter's Great Red Spot persists because it has no solid surface to create friction and slow it down. The storm feeds on smaller atmospheric disturbances, essentially consuming other storms it encounters. Think of it like a cosmic whirlpool that maintains its strength by absorbing other currents in the turbulent Jovian atmosphere. Wind speeds around the edge of the Great Red Spot reach approximately 270 miles per hour, faster than the strongest tornadoes on Earth. Yet these violent winds exist in an atmosphere with no land, no oceans, just endless layers of gas extending down into darkness. The storm rises about 5 miles above the surrounding cloud tops, creating a massive atmospheric mountain of churning gas visible from hundreds of millions of miles away. Beyond the Great Red Spot, Jupiter's atmosphere displays an incredible array of features. The planet's visible surface consists of several distinct cloud bands arranged parallel to its equator. Lighter-colored zones alternate with darker belts, creating a striped appearance that amateur astronomers can observe even with modest equipment. These bands represent different atmospheric currents, with zones being regions of upwelling gas and belts being areas where gas descends back into the planet's depths. As we descend through Jupiter's atmosphere, we encounter a world that becomes increasingly alien and extreme. The visible clouds we observe from space float in the uppermost layer of the planet's atmosphere, where temperatures hover around -240 degrees Fahrenheit. These clouds consist primarily of ammonia ice crystals, similar to how Earth's high-altitude cirrus clouds contain water ice. Below the ammonia clouds, roughly 30 to 50 miles down, lies another cloud layer. Here, temperatures and pressures have increased enough for ammonium hydrosulfide crystals to form. These clouds contribute to Jupiter's brown and tan colorations. Descending further still, about 90 miles below the visible cloud tops, we would encounter clouds of water ice and perhaps liquid water droplets. This layer exists where temperatures have warmed to near the freezing point of water, though the crushing pressure makes conditions utterly inhospitable to life as we know it. The atmosphere doesn't simply end at some definite boundary. Instead, as you descend deeper into Jupiter, the gas gradually becomes thicker and denser. About 600 miles down, the pressure becomes so immense that the hydrogen gas begins to behave less like a gas and more like a liquid. Scientists call this a supercritical fluid, a state of matter that has properties of both gases and liquids. Imagine descending through increasingly thick fog that slowly transforms into an ocean with no clear boundary between the two states. Continuing our descent, around 3,000 miles beneath the cloud tops, the pressure reaches truly staggering levels. Here, roughly 3 million times the atmospheric pressure at Earth's surface, something remarkable happens. The hydrogen undergoes a phase transition and becomes metallic hydrogen. In this exotic state, the intense pressure strips electrons from hydrogen atoms, allowing them to move freely. The hydrogen now conducts electricity like a metal, though it remains fluid rather than solid. This layer of metallic hydrogen extends through most of Jupiter's interior, reaching down approximately 35,000 miles toward the center. The metallic hydrogen layer plays a crucial role in generating Jupiter's powerful magnetic field, which we'll explore more later. But first, let's consider what lies at the very core of this giant world. At Jupiter's center, beneath all those thousands of miles of hydrogen and helium, lies a core. Scientists believe this core consists of rock, metal, and perhaps hydrogen compounds compressed into exotic states of matter. The temperature at the core likely reaches roughly 35,000 degrees Fahrenheit, hotter than the surface of our sun. The pressure is almost incomprehensible, roughly 50 million times Earth's atmospheric pressure. Under these extreme conditions, matter behaves in ways we can barely begin to understand. The core may contain 10 to 20 times the mass of Earth, though its precise composition and state remain subjects of ongoing investigation. Jupiter generates far more heat than it receives from the distant sun. The planet radiates about 1.5 times as much energy as it absorbs from sunlight. This internal heat comes from gravitational contraction. Jupiter is still very slowly shrinking, compressing under its own enormous gravity. This compression converts gravitational potential energy into thermal energy, warming the planet from within. Think of it like squeezing a stress ball. The mechanical work of compression generates a tiny bit of heat. Scale this up to planetary proportions with colossal gravitational forces, and you get a world that glows with its own internal warmth. Jupiter possesses the most powerful magnetic field of any planet in our solar system. The field extends millions of miles into space, creating an enormous magnetic bubble called a magnetosphere. If you could see Jupiter's magnetosphere glowing in the night sky from Earth, it would appear roughly 5 times larger than the full moon, despite Jupiter's immense distance from us. This magnetic realm is a dynamic, dangerous place, filled with intense radiation and charged particles. The source of this tremendous magnetic field lies deep within Jupiter, in that vast ocean of metallic hydrogen we discussed earlier. As Jupiter rotates every 10 hours, the electrically conductive metallic hydrogen swirls and flows in the planet's interior. These moving electrical charges generate powerful electrical currents, which in turn produce the magnetic field. The process works much like a dynamo or electrical generator, converting the planet's rotational energy into magnetic energy. The strength of Jupiter's magnetic field at its cloud tops is roughly 14 times stronger than Earth's magnetic field at our planet's surface. Near Jupiter's magnetic equator, the field strength reaches about 4 Gauss, compared to about half a Gauss for Earth. This might not sound dramatically different, but remember that magnetic field strength drops rapidly with distance. Jupiter's magnetic influence extends so far into space that its magnetosphere is by far the largest structure in our solar system, excluding the Sun itself. The magnetosphere traps enormous quantities of charged particles, creating radiation belts far more intense than Earth's Van Allen belts. These radiation belts contain high-energy electrons, protons, and heavier ions that whip around Jupiter at tremendous speeds. The radiation environment near Jupiter is so harsh that it poses a serious challenge for spacecraft. Several missions have had instruments damaged or disrupted by the intense radiation during close approaches to the planet. Within the magnetosphere, Jupiter's rapid rotation creates a powerful electric field. This field accelerates charged particles to extremely high energies. Some of these particles follow magnetic field lines down into Jupiter's upper atmosphere near the poles, where they collide with atmospheric molecules. These collisions excite the molecules and cause them to emit light, creating auroras far more powerful and extensive than the northern and southern lights on Earth. Jupiter's auroras are truly spectacular phenomena. They occur continuously at both poles, forming enormous glowing ovals hundreds to thousands of miles across. Unlike Earth's auroras, which brighten and fade depending on solar activity, Jupiter's main auroral ovals shine steadily, powered by the planet's rotation and magnetic field rather than solely by the solar breeze. The auroras emit light across the spectrum, from radio waves through visible light and into the ultraviolet and X-ray wavelengths. The magnetosphere interacts dramatically with Jupiter's moons, particularly Io, the volcanically active innermost Galilean moon. Io orbits within Jupiter's intense radiation belts and continuously spews out sulfur and oxygen from its numerous volcanoes. These materials become ionized and form a torus, a donut-shaped cloud of charged particles, around Jupiter along Io's orbital path. This Io plasma torus adds additional complexity to Jupiter's magnetosphere and creates electrical currents flowing between Jupiter and Io. In January of 1610, Galileo Galilei pointed his telescope at Jupiter and made a discovery that would change our understanding of the cosmos. He observed 4 points of light near Jupiter that moved from night to night, clearly orbiting the giant planet. These 4 moons, now called the Galilean satellites in his honor, are Io, Europa, Ganymede, and Callisto. Each is a world unto itself, with unique characteristics and mysteries that continue to intrigue scientists today. Io, the innermost Galilean moon, is the most volcanically active body in the entire solar system. More than 400 active volcanoes surface, constantly resurfacing the moon with fresh lava flows and sulfurous compounds. Io's volcanic fury stems from tidal heating. As Io orbits Jupiter, the giant planet's enormous gravity pulls on the moon, flexing and squeezing it like a rubber ball. The other Galilean moons, particularly Europa and Ganymede, add their own gravitational tugs, maintaining Io in a slightly elliptical orbit that ensures the tidal flexing never stops. This constant kneading generates tremendous heat inside Io, melting rock and driving the spectacular volcanic activity. The volcanic plumes on Io can reach heights of 200 miles or more above the surface, ejecting material into space at speeds up to half a mile per second. These eruptions coat Io's surface with sulfur dioxide frost, and other volcanic materials, giving the moon its distinctive yellow, orange, red, and white appearance. Imagine a world painted with the colors of autumn leaves and desert sunsets, constantly renewing itself through fire and brimstone. Europa, the second Galilean moon, presents a completely different character. This moon is covered by a smooth shell of water ice, crisscrossed with dark linear features called lineae. The surface is remarkably young in geological terms, with very few impact craters suggesting the ice is constantly renewed. Beneath this frozen shell, strong evidence suggests a global ocean of liquid water exists, perhaps containing twice as much water as all of Earth's oceans combined. The ice shell on Europa may be 10 to 15 miles thick in most places, though some regions might be considerably thinner. Below this ice, the ocean could be 50 to 100 miles deep, in direct contact with a rocky seafloor. This configuration is particularly exciting for astrobiologists because the interaction between water and rock can provide chemical energy and nutrients. On Earth, similar environments at the bottom of our oceans, near hydrothermal vents, support thriving ecosystems completely independent of sunlight. Could Europa's ocean harbor life? We don't know yet, but the possibility has made Europa a prime target for future exploration. The dark lines crisscrossing Europa's surface tell a story of ice tectonics and possible cryovolcanism. Some of these features appear to be places where the ice shell has cracked, separated, and been filled in with warmer ice or possibly liquid water from below. Others might be locations where slushy ice or liquid water has erupted onto the surface, similar to how volcanoes work on Earth, but with water instead of molten rock. Scientists have also detected possible water vapor plumes erupting from Europa's surface, though these observations require confirmation. Ganymede, the largest moon in our solar system, exceeds even the planet Mercury in size. This enormous satellite has a diameter of 3,273 miles, making it larger than the planet Pluto. Ganymede is the only moon known to have its own intrinsic magnetic field, likely generated by a liquid iron core. This magnetic field creates a small magnetosphere within Jupiter's much larger one, a unique configuration found nowhere else in our solar system. Ganymede's surface displays a fascinating mix of ancient dark terrain and younger bright terrain. The dark regions are heavily cratered and very old, perhaps dating back 4 billion years. The bright terrain is younger and features extensive grooves and ridges, suggesting periods of geological activity that reshaped portions of the moon's surface. Like Europa, Ganymede likely harbors a subsurface ocean, sandwiched between layers of ice at different pressures and temperatures. This ocean might lie roughly 100 miles beneath the surface, insulated by the ice above. Callisto, the outermost Galilean moon, orbits Jupiter at a distance of roughly 1,200,000 miles. This distant orbit places Callisto just outside the most intense regions of Jupiter's radiation belts, making it a potentially safer destination for future human missions to the Jovian system. Callisto is the third largest moon in our solar system and has the oldest, most heavily cratered surface of any body yet observed. The sheer number of craters covering Callisto's surface tells us that geological activity essentially ceased there billions of years ago. Unlike Io, Europa, and Ganymede, which show various signs of internal heat and geological processes, Callisto appears to be a frozen, inactive world. Its surface is a mixture of ice and rock, darkened by eons of impacts and space weathering. Think of it as a cosmic museum, preserving a record of the solar system's violent early history when impacts were far more common than today. Despite its ancient, inactive appearance, Callisto may also hide a subsurface ocean. Magnetic field measurements by spacecraft suggest the presence of a salty, electrically conducting layer beneath the surface. This ocean, if it exists, might lie 100 to 200 miles below the ice and rock surface. The heat to maintain such an ocean could come from radioactive decay in Callisto's rocky interior and from tidal heating, though the tidal forces affecting Callisto are much weaker than those experienced by the inner Galilean moons. Beyond the 4 Galilean moons, Jupiter hosts dozens of smaller satellites. As of the latest counts, astronomers have discovered 79 confirmed moons orbiting Jupiter, and more tiny ones are probably waiting to be found. Most of these smaller moons are irregular satellites, likely asteroids that were captured by Jupiter's powerful gravity long ago. They orbit in distant, tilted, and often retrograde paths, moving in the opposite direction to Jupiter's rotation and the Galilean moon's orbits. Jupiter also possesses a faint ring system, discovered by the Voyager 1 spacecraft in 1979. Unlike Saturn's magnificent, bright rings, Jupiter's rings are tenuous and difficult to observe. The main ring lies about 81,000 miles from Jupiter's center, roughly 36,000 miles above the cloud tops. This ring consists of fine dust particles knocked off small moons by micrometeorite impacts. The ring system actually has several components. The main ring is bounded by 2 small moons, Adristiet and Métis, which orbit within the ring itself. Anterior to the main ring is a thick torus of particles called the halo ring. This structure extends inward toward Jupiter, puffed up by the planet's magnetic field acting on electrically charged dust grains. Beyond the main ring, 2 faint gossamer rings stretch outward, associated with the small moons Amalthea and Thebe. Material knocked off these moons by impacts drifts inward toward Jupiter, forming these extended, diffuse rings. The particles in Jupiter's rings are tiny, typically less than a few microns across, about the size of smoke particles. These microscopic grains scatter light differently than the larger ice chunks in Saturn's rings, which is why Jupiter's rings appear reddish in reflected sunlight and bright when backlit. The rings are constantly being replenished by impacts on the small inner moons and are relatively short-lived on cosmic timescales. Without this constant supply of fresh material, Jupiter's rings would disappear in just a few thousand years, swept away by atmospheric drag and other forces. The entire system of moons and rings creates a dynamic, interconnected environment around Jupiter. The moons gravitationally perturb each other's orbits, clear gaps in the rings, and supply material to both the rings and Jupiter's magnetosphere. Meanwhile, Jupiter's powerful magnetic field and rapid rotation shaped the behavior of charged particles throughout the system, creating a cosmic laboratory unlike anything else in our solar system. Humanity's exploration of Jupiter began with naked-eye observations thousands of years ago. Ancient civilizations knew Jupiter as a bright wandering star moving through the night sky. The Babylonians tracked its movements carefully, and many cultures associated the planet with their chief deities. The modern name Jupiter comes from the king of the Roman gods, a fitting name for the king of planets. The invention of the telescope revolutionized our view of Jupiter. When Galileo first observed the planet and its 4 large moons in 1610, he provided crucial evidence for the Copernican model of the solar system. If moons could orbit Jupiter, then clearly not everything revolved around Earth. This observation helped shift humanity's cosmic perspective from an Earth-centered universe to our modern understanding of a vast cosmos in which Earth is one planet among many. Through the 17th, 18th, and 19th centuries, astronomers using increasingly powerful telescopes mapped Jupiter's cloud bands and tracked the Great Red Spot. They measured Jupiter's rotation period, determined its mass and density, and began to understand its composition. Spectroscopy, the analysis of light broken into its component colors, revealed the presence of hydrogen, helium, methane, and ammonia in Jupiter's atmosphere. The space age brought unprecedented close-up views of Jupiter. Pioneer 10 flew past Jupiter in December of 1973, followed by Pioneer 11 in December of 1974. These spacecraft returned the first close-range images of the planet and its moons, measured its magnetic field and radiation belts, and provided valuable data about the Jovian environment. The missions proved that spacecraft could survive passage through Jupiter's intense radiation belts, paving the way for future exploration. The Voyager missions in 1979 transformed our understanding of the Jupiter system. Voyager 1 and Voyager 2 conducted detailed studies of the planet, its atmosphere, magnetosphere, rings, and moons. The Voyager images revealed volcanoes on Io, the first active volcanoes discovered beyond Earth. They showed Europa's intriguing icy surface, mapped Ganymede's varied terrain, and cataloged Callisto's ancient craters. The discoveries from Voyager continue to drive scientific investigation decades later. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided years of detailed observations. Galileo watched the impact of Comet Shoemaker-Levy 9 in 1994, when more than 20 comet pieces crashed into Jupiter's atmosphere, creating enormous dark scars visible even from Earth. The spacecraft made multiple close flybys of the Galilean moons, gathering data that revealed the probable subsurface oceans on Europa and Ganymede. Galileo also dropped a probe into Jupiter's atmosphere, which transmitted data for about an hour as it descended before being crushed by the increasing pressure. More recent missions have continued the exploration. The Cassini spacecraft flew past Jupiter in 2000 while en route to Saturn, conducting joint observations with Galileo. The New Horizons spacecraft used Jupiter for a gravity assist in 2007, studying the planet's atmosphere and magnetosphere during its flyby. The Juno mission, which arrived at Jupiter in 2016, is currently in orbit studying the planet's deep interior structure, magnetic field, and polar regions with unprecedented detail. Juno's highly elliptical orbit carries it from just above Jupiter's cloud tops to far beyond the orbits of the Galilean moons. During each close approach, Juno speeds over the poles at roughly 130,000 miles per hour, gathering data on Jupiter's gravity field, magnetic field, atmospheric composition, and interior structure. These measurements are helping scientists understand how Jupiter formed, what lies at its core, and how its spectacular auroras are powered. Jupiter's role extends far beyond being merely the largest planet in our solar system. The giant planet has profoundly influenced the architecture and evolution of our entire planetary system. Its enormous gravitational pull has acted like a cosmic shepherd, affecting the orbits of asteroids, comets, and even the other planets since the solar system's formation 4.5 billion years ago. The asteroid belt, located between Mars and Jupiter, exists largely because of Jupiter's influence. Early in solar system history, material in this region might have coalesced into another planet. However, Jupiter's powerful gravity stirred up the orbits of these building blocks, causing them to collide at high speeds that shattered them rather than allowing them to gently stick together and grow. The result is a ring of millions of asteroids that represents the remnants of a planet that never formed. Jupiter also acts as a cosmic vacuum cleaner, or, more accurately, a gravitational shield for the inner solar system. Its immense mass helps deflect or capture many comets and asteroids that would otherwise potentially threaten Earth and the other terrestrial planets. The impact of Comet Shoemaker-Levy 9 in 1994 provided a dramatic demonstration of this protective role. Had Jupiter not been there, some of those comet pieces might eventually have found their way to the inner solar system. However, Jupiter's influence is not entirely protective. The giant planet's gravity also perturbs some objects onto orbits that bring them into the inner solar system. The relationship is complicated, with Jupiter both shielding us from some impacts and causing others. Overall, scientists debate whether Jupiter's presence has significantly reduced Earth's impact rate, but there is no question that the giant planet has shaped the population and dynamics of small bodies throughout the solar system. Looking beyond our own solar system, Jupiter has become a template for understanding giant planets around other stars. Astronomers have discovered thousands of planets orbiting distant stars, and many of these are gas giants similar to Jupiter. Some, called hot Jupiters, orbit extremely close to their parent stars, completing their orbits in just a few days. These configurations surprised astronomers, who initially expected other solar systems to resemble our own, with giant planets in distant orbits. The existence of hot Jupiters has led to new theories about planet formation and migration. Giant planets may form in the outer reaches of their planetary systems, then gradually spiral inward through gravitational interactions with the disk of gas and dust that initially surrounds young stars. This process of planetary migration has important implications for the habitability of planetary systems. If a giant planet migrates inward, it could disrupt or eject rocky planets from stable orbits, dramatically affecting whether life has a chance to develop. Studying Jupiter thus provides insights relevant to planetary systems throughout our galaxy. The techniques developed to study Jupiter's atmosphere, interior structure, and magnetic field can be adapted to study similar planets light years away. Every new discovery about Jupiter informs our broader understanding of how planets form, evolve, and interact with their environments. Jupiter also serves as a natural laboratory for studying extreme physics and chemistry. The conditions inside Jupiter, with pressures millions of times Earth's atmospheric pressure and temperatures rivaling the Sun's surface, cannot be recreated in laboratories on Earth. By studying Jupiter, scientists can test theoretical models of matter under extreme conditions, models that apply to everything from the interiors of stars to the earliest moments after the Big Bang. The magnetic fields, auroras, and charged particle environments around Jupiter help scientists understand similar processes throughout the universe. Magnetic fields play crucial roles in star formation, in the behavior of accretion disks around black holes, and in the dynamics of entire galaxies. Jupiter's magnetosphere, accessible to our spacecraft and instruments, provides a nearby example of these universal physical processes in action. Perhaps most intriguingly, the Galilean moons, especially Europa and potentially Ganymede and Callisto, offer possible environments where life could exist beyond Earth. The search for life elsewhere in the universe is one of the most profound scientific endeavors of our time. While Mars often captures headlines in this search, the icy moons of Jupiter may actually offer the best near-term prospects for discovering existing life in our solar system. The combination of liquid water, chemical energy sources, and sufficient time for life to develop makes these moons compelling targets for future missions specifically designed to search for biosignatures or even direct evidence of microbial life. And on that note, we conclude our peaceful journey through the realm of Jupiter. From its swirling storms and hidden depths to its magnificent moons and powerful magnetic field, Jupiter reveals itself as a world of superlatives and surprises. This giant planet continues to challenge our understanding and inspire our curiosity about the cosmos. Saturn has been known to humanity since before recorded history began. Ancient civilizations noticed this bright point of light moving slowly against the backdrop of fixed stars, taking nearly 30 years to complete one orbit around the Sun. The Babylonians associated it with their god of justice and fairness, while the Romans named it after their god of agriculture and time. When Galileo Galilei first turned his telescope toward Saturn in 1610, he saw something peculiar. The resolution of his instrument wasn't quite good enough to reveal the true nature of the rings, so he described Saturn as having ears or appearing triple-bodied. It wasn't until 1655 that Christiaan Huygens, using a more powerful telescope, correctly identified these features as a disk or ring surrounding the planet. Saturn resides approximately 1.4 billion kilometers from the Sun, which is about 9.5 times the distance between Earth and the Sun. At this remote location, sunlight takes around 80 minutes to reach Saturn's clouds, compared to just 8 minutes for Earth. This great distance means Saturn receives only about 1% of the sunlight that bathes our home planet. Despite this faint illumination, Saturn shines brightly in our night sky, typically appearing as a steady, yellowish point among the stars. The planet itself is enormous. Its equatorial diameter measures roughly 120,000 kilometers, making it about 9.5 times wider than Earth. If Earth were the size of a marble, Saturn would be comparable to a basketball. Yet despite its tremendous size, Saturn has a remarkably low density. The planet's average density is only about 0.69 grams per cubic centimeter, which is less dense than water. If you could find an ocean large enough, Saturn would actually float. This low density tells us something fundamental about Saturn's composition. The planet is made primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Saturn completes one rotation on its axis in just 10 hours and 33 minutes, making its day less than half the length of an Earth day. This rapid rotation causes the planet to bulge noticeably at its equator and flatten at its poles. The equatorial diameter is about 10% larger than the polar diameter, giving Saturn a distinctly oblate shape that's visible even in small telescopes. This spinning motion also drives powerful winds in Saturn's atmosphere, creating the bands and zones we observe wrapping around the planet. Saturn belongs to a class of planets called gas giants, though this name is somewhat misleading. While the outer layers are indeed gaseous, the conditions deeper within the planet are far more unusual. Let's take an imaginary descent through Saturn's structure, moving from the cloud tops down toward the mysterious core. The visible surface of Saturn, the layer we see in photographs isn't a solid surface at all. It's the top of a thick atmosphere composed of approximately 96% hydrogen and 3% helium, with traces of methane, ammonia, water vapor, and other compounds. The temperature at this level, where atmospheric pressure equals Earth's sea level pressure, hovers around -139 degrees Celsius. The pale yellow and gold colors we observe come from ammonia crystals and other compounds in the upper atmosphere. These clouds organize themselves into bands that circle the planet, driven by Saturn's rapid rotation and internal heat. As we descend deeper into Saturn, the pressure and temperature steadily increase. The atmosphere grows denser, gradually transitioning from gas to liquid without any clear boundary. Around 1,000 kilometers below the cloud tops, the pressure becomes so intense that hydrogen begins to behave in unusual ways. By the time we reach depths of about 10,000 kilometers, where pressures exceed 1 million times Earth's surface pressure and temperatures climb to several thousand degrees, hydrogen transforms into a metallic state. This isn't metal in the everyday sense of the word. Instead, the hydrogen atoms are squeezed so tightly together that their electrons break free and move about independently, allowing the substance to conduct electricity like a metal does. This layer of metallic hydrogen makes up the bulk of Saturn's interior and extends perhaps halfway to the center of the planet. The presence of this electrically conductive layer is crucial because it generates Saturn's magnetic field. As the planet rotates, electric currents flow through this metallic hydrogen, creating a magnetic field that extends far out into space, though it's notably weaker than Jupiter's field. At the very center of Saturn, under pressures millions of times greater than Earth's atmosphere and at temperatures approaching 12,000 degrees Celsius, lies what scientists believe to be a core of rock, metal, and ice. This core probably has a mass between 15 and 20 times that of Earth. The term ice here doesn't mean frozen water as we know it. Under such extreme conditions, materials like water, methane, and ammonia exist in hot, dense forms that bear little resemblance to the ice in your freezer. One of Saturn's most intriguing characteristics is that it radiates about 2.5 times more energy into space than it receives from the Sun. This extra energy comes from the planet's interior. Saturn is still slowly contracting from its formation 4.5 billion years ago, and this gradual compression converts gravitational potential energy into heat. Think of it like a giant, slow-motion version of pumping up a bicycle tire, where compressing the gas makes it warmer. This internal heat source drives much of the weather and atmospheric dynamics we observe on Saturn. Saturn's atmosphere is a dynamic realm of winds, storms, and subtle color variations. The banded appearance of the planet results from different atmospheric zones moving at different speeds. The bright zones are regions of rising gas, where ammonia ice crystals form at high altitudes, creating pale clouds. The darker belts are areas where gas descends, clearing away the high-altitude clouds and revealing the deeper, darker layers beneath. The winds on Saturn are among the fastest in the solar system. Near the equator, winds can reach speeds of about 1,800 kilometers per hour, which is roughly 5 times faster than the strongest hurricanes on Earth. These powerful jet streams circle the planet in alternating eastward and westward directions, with each band maintaining its own speed and direction for decades or longer. The energy driving these winds comes from both the Sun's heating and Saturn's internal heat source. Saturn occasionally produces massive storms that erupt in its upper atmosphere. The most famous of these are the Great White Spots, enormous storms that appear roughly once every Saturnian year, or about every 30 Earth years. These storms develop in Saturn's northern hemisphere during its summer season and can grow to encircle the entire planet. The The storm of 2010 and 2011 was particularly spectacular, eventually stretching more than 300,000 kilometers around the planet's circumference. These tempests are thought to be convective events, where warm gas from deep in the atmosphere rises explosively through cooler layers above, creating towering thunderstorms and turbulent winds. At Saturn's North Pole sits one of the solar system's most geometrically peculiar features, a massive hexagonal jet stream. Each side of this hexagon spans about 13,800 kilometers, wider than Earth's diameter. The hexagon rotates with a period of 10 hours and 39 minutes, slightly slower than the planet's interior rotation. Scientists have studied this feature extensively since its discovery by the Voyager spacecraft in the early 1980s, and it has remained remarkably stable for decades. The hexagon is essentially a standing wave pattern in the jet stream, a phenomenon that can be reproduced in laboratory experiments with rotating fluids. Inside this hexagonal structure lies a swirling vortex, a hurricane-like storm anchored at the pole itself. The South Pole hosts a more conventional but equally impressive feature, a hurricane-like vortex with a well-defined and measuring about 8,000 kilometers across. Unlike hurricanes on Earth, which derive their energy from warm ocean water, this polar vortex is powered by Saturn's internal heat and the dynamics of the atmosphere itself. Saturn's atmosphere also produces lightning, though it's quite different from terrestrial lightning. The lightning on Saturn occurs deep within the clouds, producing radio bursts that spacecraft can detect. Individual storms can produce lightning bolts thousands of times more powerful than those on Earth, with some storms generating continuous electrical activity for months. These electrical discharges are associated with the convective storms that occasionally erupt in Saturn's atmosphere, where rapid updrafts and downdrafts cause ice particles to collide and build up electrical charges. Saturn's rings are perhaps the most recognizable feature in the entire solar system. Extending outward from the planet for hundreds of thousands of kilometers, yet often measuring only 10 to 30 meters thick in most places, the rings create a stunning disk that appears almost impossibly thin when viewed edge-on. These rings aren't solid structures, but rather countless individual particles, ranging in size from tiny grains smaller than sand to chunks larger than houses, all orbiting Saturn independently. The main ring system consists of several distinct regions, designated by letters in the order they were discovered rather than their position. Starting from the planet and moving outward, the main rings are Ring D, Ring C, Ring B, Ring A, Ring F, Ring G, and Ring E. Ring C appears somewhat transparent and ghostly, earning it the nickname Crepe Ring. Ring B is the brightest and most massive of the rings, containing the majority of the ring system's total mass. A dark gap called the Cassini division, about 4,800 kilometers wide, visually divides Ring B from Ring A. The Cassini division isn't completely empty but contains less material than the brighter regions on either side. The composition of the ring particles is primarily water ice, which explains why the rings are so bright and reflective. The ice is remarkably pure, reflecting between 60 and 90% of the sunlight that strikes it. Mixed with the ice are smaller amounts of rocky material and organic compounds that give some rings a slightly darker or more tan appearance. The particles are distributed in intricate patterns, tight spirals, rippling waves, narrow strands, and knotted clumps that shift and change over time. One of the most fascinating aspects of Saturn's rings is their surprising youth. Several lines of evidence suggest the rings may be only 10 million to 100 million years old, far younger than the solar system itself or even the age of Saturn. The rings are simply too bright and clean to be ancient. Over time, ring particles should become darkened by bombardment from meteoroids and coated with dust from comets, yet Saturn's rings remain brilliantly reflective. This suggests either the rings formed relatively recently or some process continually cleans and rejuvenates them. How did the rings form? Scientists have several theories. The rings might be the remains of a moon that wandered too close to Saturn and was torn apart by tidal forces. There's a distance from any planet, called the Roche limit, inside which tidal forces become stronger than the gravity holding a moon together. For Saturn, this distance is about 2.4 times the planet's radius, and most of the bright rings lie within this zone. Alternatively, the rings might have formed from debris left over from a collision between two moons, or from a comet that strayed too close and was shredded by Saturn's gravity. The intricate structure of the rings results from gravitational interactions with Saturn's many moons. Some small moons orbit within the rings themselves, called embedded moons, and their gravity creates gaps and waves in the surrounding material. Other moons orbit just beyond the main rings, and their repeated gravitational tugs shepherd ring particles into narrow bands or clear out gaps. Ring F, for example, is confined by two shepherd moons named Prometheus and Pandora, whose gravity keeps the ring particles in a narrow band. The relationship between Saturn's rings and its moons creates some of the most intricate dynamics in the solar system. Dozens of small moons orbit among and near the rings, and their gravitational influence sculpts the ring material into elaborate patterns. Understanding these interactions requires us to think about how gravity works not just as a simple attractive force, but as something that can push, pull, shape, and organize matter across vast distances. Consider the Cassini division, that prominent dark gap in the rings. While it appears empty from a distance, it actually contains some ring material, just much less than the bright regions on either side. The reason for this relative emptiness is a gravitational resonance with Mimas, one of Saturn's inner moons. Particles orbiting in the Cassini division complete exactly 2 orbits around Saturn for every 1 orbit of Mimas. This 2-to-1 resonance means particles encounter Mimas's gravitational pull at the same point in their orbit repeatedly, and these repeated tugs gradually nudge the particles into different orbits, clearing out the gap over time. It's similar to pushing someone on a swing. If you push at just the right moment with each swing, your repeated small pushes can create a large effect. The moon Prometheus provides another beautiful example of gravitational sculpting. Prometheus orbits just inside ring F, and as it passes ring particles, its gravity pulls some of them inward, creating dark channels in the ring. These channels appear as dark streaks that follow behind the moon, marking its gravitational wake through the ring material. Because Prometheus and the ring particles move at slightly different speeds, these streaks slowly shift and blur over time, creating a pattern that changes from month to month. Some of Saturn's smallest moons actually orbit within the rings themselves. Pan, a small moon just 28 kilometers across, orbits within the Inky Gap, a 325-kilometer wide opening in Ring A. Pan's gravity keeps this gap clear of ring particles, but it does more than that. Ring material near the gap edge gets pulled toward Pan, creating wave patterns that ripple through the rings like wakes behind a boat. These waves can be seen in detailed images as subtle corrugations extending outward from the gap. Another embedded moon, Daphnis, orbits within the Keeler Gap in the outer Ring A. Daphnis is even tinier than Pan, measuring only about 8 kilometers across, yet its gravity is sufficient to create magnificent wave patterns at the edges of its gap. The waves reach heights of up to 1.5 kilometers above the ring plane, creating scalloped patterns that look almost like a decorative edging. The outermost regions of Saturn's ring system are even more diffuse and extended. Ring E, for instance, stretches from about 180,000 to 480,000 kilometers from Saturn's center, making it by far the largest ring. Unlike the main rings, which are confined to a thin plane, Ring E has significant vertical thickness, perhaps exceeding 2,000 kilometers in height. This ring is continuously supplied with material from the moon Enceladus, which orbits within it. Enceladus spews water vapor and ice particles into space through geysers at its south pole, and this material spreads out to form Ring E. Ring F deserves special mention for its bizarre and ever-changing appearance. This narrow ring, located just beyond the outer edge of Ring A, displays braids, kinks, and clumps that shift dramatically over short timescales. Ring F seems to be in a constant state of disruption and reorganization. Small moonlets embedded within the ring, perhaps 10 to 100 meters across, collide with ring particles, creating temporary clumps and streamers. The two shepherd moons, Prometheus and Pandora, continually perturb the ring from inside and outside, adding to the chaos. Recent observations suggest that Ring F might be fed by material pulled off the surfaces of these small moonlets when they collide with other ring particles. Saturn's family of moons is one of the most diverse and fascinating in the solar system, with 146 confirmed moons as of current counts, ranging from tiny, irregular chunks of rock and ice just a few kilometers across to the giant moon Titan, which is larger than the planet Mercury. These moons formed from the same disk of material that created Saturn itself, though some of the smaller, more distant moons may be captured asteroids or comets. Titan stands apart as the second largest moon in the solar system and the only moon with a thick atmosphere. With a diameter of 5,150 kilometers, Titan is about 1.5 times larger than Earth's moon. What makes Titan truly exceptional is its dense nitrogen atmosphere, which is actually thicker than Earth's atmosphere at the surface. The atmospheric pressure at Titan's surface is about 1.5 times Earth's sea level pressure. This thick atmosphere creates a haze of organic molecules that completely obscures the surface in visible light, giving Titan a featureless, orange appearance through conventional telescopes. The temperature on Titan's surface hovers around -179 degrees Celsius, cold enough that water ice is as hard as rock. At these frigid temperatures, methane and ethane can exist as liquids, and Titan has weather systems and a hydrological cycle based on these hydrocarbons rather than water. Radar observations from the Cassini spacecraft revealed lakes and seas of liquid methane and ethane near Titan's poles, some of them hundreds of kilometers across. Titan has rain, rivers, and coastlines, all shaped by flowing liquid hydrocarbons. The Huygens probe, which landed on Titan in 2005, revealed a surface of rounded pebbles made of water ice, shaped by flowing liquid methane. Titan's thick atmosphere and surface conditions make it one of the most Earth-like worlds in the solar system, despite the extremely cold temperatures and exotic chemistry. The moon has seasons, clouds, and even dust storms. Organic chemistry proceeds vigorously in Titan's atmosphere, creating molecules that rain down onto the surface and may accumulate in lakes and seas. Some scientists speculate that Titan could harbor unusual forms of life based on liquid methane rather than water, though this remains purely theoretical. Moving inward from Titan, we encounter Enceladus, a small moon only about 500 kilometers in diameter, but arguably even more exciting than Titan for the search for life. In 2005, the Cassini spacecraft made a startling discovery: massive geysers of water vapor and ice particles erupting from cracks near Enceladus's south pole. These geysers shoot material hundreds of kilometers into space at speeds of up to 400 meters per second, with some particles escaping Enceladus entirely to feed Saturn's Ring E. The source of these geysers appears to be a subsurface ocean of liquid water beneath Enceladus's icy crust. Tidal heating from Saturn keeps this ocean liquid despite the moon's small size and frigid location. As Enceladus orbits Saturn, gravitational forces flex and squeeze the moon, generating heat through friction. This is similar to how repeatedly bending a wire back and forth makes it warm up. The geysers erupt from 4 prominent cracks near the South Pole, nicknamed the Tiger Stripes, where the ice is thinner and fractured. What makes Enceladus especially intriguing is that Cassini detected organic molecules, salts, and molecular hydrogen in the geyser plumes. The presence of hydrogen suggests chemical reactions between the ocean water and hot rocks on the seafloor, reactions that could provide energy for microbial life. All the key ingredients for life as we know it appear to be present in Enceladus's ocean: liquid water, organic molecules, and an energy source. Other notable moons include Mimas, famous for its giant impact crater that makes it resemble a certain fictional space station, Iapetus with its mysterious 2-tone coloration, one hemisphere bright and one dark, and Tethys with its enormous canyon system stretching nearly 3/4 of the way around the moon. Each of these moons tells a story about the history of the Saturn system, recording impacts, tidal forces, and geological processes in their scarred and varied surfaces. To understand Saturn and its system of rings and moons, we need to travel back more than 4.5 billion years to the birth of the solar system. Our solar system formed from a vast cloud of gas and dust, perhaps 10,000 times more massive than the Sun is today. Something, perhaps a nearby supernova or the passage of a shock wave through the galaxy, caused this cloud to begin collapsing under its own gravity. As the cloud collapsed, it began to spin faster, much like a figure skater spins faster when pulling in their arms. This rotation caused the cloud to flatten into a rotating disk with a dense, hot center where the Sun would eventually ignite. In the disk surrounding the young Sun, dust grains began sticking together through collisions, gradually building up larger and larger clumps. Close to the Sun, where temperatures were high, only materials with high melting points like rock and metal could remain solid. Further out, beyond what scientists call the frost line, temperatures were low enough for water ice to remain frozen. Saturn formed in this cold, outer region of the disk where ice was abundant. The process likely began with a solid core of rock and ice, perhaps 10 to 20 times Earth's mass, that formed relatively quickly over a few million years. Once this core grew large enough, its gravity became strong enough to capture and hold onto the abundant hydrogen and helium gas in the surrounding disk. Over perhaps another few million years, this core accumulated an enormous envelope of gas, growing into the giant planet we see today. The timing was crucial. Giant planets like Saturn had to form quickly, within about 10 million years, before the gas in the disk was either swept up by the Sun or blown away by solar radiation and stellar winds. Jupiter, being closer to the Sun where the disk was denser, likely formed first and faster. Saturn followed, but by the time it was growing, less gas remained available, which may explain why Saturn is smaller and less massive than Jupiter. Saturn's rings and moons likely formed from the same disk of material that surrounded Saturn during its growth. The moons grew from countless collisions of smaller bodies, gradually sweeping up material in their orbital zones. The rings may be younger, perhaps formed much later from a destroyed moon or a captured comet. The exact sequence of events remains a subject of active research and debate. Over the billions of years since formation, Saturn has slowly evolved. The planet continues to contract very gradually, releasing the internal heat that powers its atmospheric dynamics. The rings have probably changed significantly, perhaps being destroyed and reformed multiple times over Saturn's history. Moons have shifted their orbits through tidal interactions with Saturn and with each other. Some moons may have formed where they are now, while others may have migrated inward or outward over time. Recent research suggests that Saturn's rings may be quite young, perhaps only 100 million years old or less. If true, this means Earth's dinosaurs might have lived under a ringless Saturn, and the magnificent ring system we see today is a relatively recent addition to the solar system. The implications are profound. If rings are temporary features that come and go, then we're fortunate to live in an era when Saturn possesses such a spectacular display. For thousands of years, humans observed Saturn as simply a bright, yellowish point of light moving slowly against the stars. Everything changed when the telescope was invented in the early 17th century. Galileo's first observations in 1610 were puzzling, as his small telescope showed Saturn as having two strange appendages or bulges that he couldn't quite resolve. By 1612, these features had disappeared, which thoroughly confused Galileo. We now know he was seeing the rings at different angles as Saturn moved in its orbit. When the rings were nearly edge onto Earth, they effectively vanished from view in his small telescope. Christian Huygens solved the puzzle in 1655, proposing that Saturn was surrounded by a thin, flat ring. Giovanni Domenico Cassini discovered the gap in the rings that now bears his name, and realized the rings must be composed of countless small particles rather than a solid disk. As telescopes improved through the 18th and 19th centuries, astronomers discovered more moons and detected additional structure in the rings. The space age brought unprecedented views of Saturn. Pioneer 11 flew past Saturn in 1979, providing the first close-up images. Voyager 1 arrived in 1980, followed by Voyager 2 in 1981. These spacecraft revealed Saturn's atmosphere, rings, and moons in stunning detail, discovering new moons, ring features, and atmospheric phenomena. The images transmitted by Voyager remain iconic even today. The Cassini spacecraft, which arrived at Saturn in 2004, represented a quantum leap in our understanding of the Saturn system. For 13 years, Cassini orbited Saturn, observing seasonal changes, discovering new moons, studying Titan in detail, and making the groundbreaking discoveries at Enceladus. The spacecraft completed 294 orbits of Saturn before deliberately diving into the planet's atmosphere in 2017 to avoid any possibility of contaminating Enceladus with microbes from Earth. From Earth, Saturn remains an impressive target for amateur astronomers. Even a small telescope reveals the rings and can show the gap between Ring A and Ring B on nights of steady atmospheric conditions. Larger telescopes reveal cloud bands in the atmosphere and several of Saturn's larger moons. The best time to observe Saturn is when it reaches opposition, the point when Earth passes between Saturn and the Sun, placing Saturn opposite the Sun in our sky and at its closest approach to Earth for that year. The view of Saturn changes dramatically over time due to the tilt of Saturn's rotation axis. Saturn's axis is inclined about 27 degrees from perpendicular to its orbit, similar to Earth's 23.5 degree tilt. This means Saturn experiences seasons, each lasting about 7 Earth years. As Saturn moves around the Sun, we see the rings from different angles. At some points, the rings appear wide open, tilted toward us at their maximum angle. About 15 years later, we see the rings edge on, and they seem to vanish because they're so thin. Then over the next 15 years, the rings gradually open up again, but this time we see them tilted from the opposite side. Future missions to Saturn are in the planning stages. A proposed mission called Dragonfly, currently scheduled for launch in 2028, would send a rotorcraft lander to explore Titan. This flying probe would take advantage of Titan's thick atmosphere and low gravity to fly between multiple landing sites, studying the moon's organic chemistry and searching for signs of prebiotic processes. Another proposed mission would focus on Enceladus, perhaps orbiting the moon to study its geysers in detail or even landing to search for signs of life in the subsurface ocean. Saturn continues to surprise us with each new observation. Recent studies using data from Cassini have revealed that Saturn's rotation period is harder to measure than scientists expected, that the rings may be influencing Saturn's upper atmosphere, and that the planet's magnetic field is remarkably symmetrical. Each answer leads to new questions, ensuring that Saturn will remain a focus of planetary science for generations to come. And on that note, we conclude our peaceful journey through the Saturn system. We've traveled from the ancient observations that first identified Saturn as a wanderer among the stars, down through the layers of its vast atmosphere to the metallic hydrogen ocean within, across the shimmering rings with their intricate structures and embedded moons, and out to the diverse family of satellites that includes the enigmatic Titan and the potentially life-harboring Enceladus. We've explored how this magnificent planet formed in the early solar system, how it continues to evolve today, and how future missions may unlock even more of its secrets. Saturn reminds us that our solar system contains worlds of astonishing beauty and wonder, each with its own story to tell. The rings that grace Saturn are unique in their prominence and accessibility, offering us a window into orbital dynamics and gravitational interactions that play out across the cosmos. The moons surrounding Saturn represent laboratories for understanding ice, organic chemistry, and even the possibility of life in environments radically different from Earth. Imagine the night sky as astronomers knew it for thousands of years. 5 wandering stars, the planets visible to the naked eye, moved against the fixed background of constellations. Mercury, Venus, Mars, Jupiter, and Saturn were the known boundaries of our solar system. Then, on a clear March evening in 1781, a musician and amateur astronomer named William Herschel was surveying the sky from his garden in England. Using a telescope he'd built himself, a reflector with mirrors he'd carefully ground and polished, Herschel noticed something unusual in the constellation Gemini. At first, he thought it might be a comet. The object appeared as a small disk rather than a point of light, which was odd for a star. Herschel noted its position and returned to it on subsequent nights. The object moved, but not in the way comets typically moved. Its path was too slow, too circular. Other astronomers across Europe turned their instruments toward this curiosity. Calculations of its orbit revealed something extraordinary. This was no comet. Herschel had discovered a new planet, the first planet found in recorded history that hadn't been known to ancient civilizations. The discovery doubled the known size of the solar system in an instant. Saturn had marked the outer boundary at roughly 930 million miles from the Sun. This new world orbited at approximately 1,784 million miles out, nearly twice as far. The finding was so significant that it made Herschel famous across Europe. King George III of England granted him a royal pension, allowing him to pursue astronomy full-time. The question of what to name this new planet sparked debate. Herschel, hoping to honor his patron, suggested Georgium Sidus, or George's star. Others proposed Herschel itself. But ultimately, tradition won out. Just as Jupiter was named for the king of the Roman gods and Saturn for Jupiter's father, this new planet would be named for Saturn's father in mythology. Uranus, the ancient Greek deity of the sky, gave his name to this distant, mysterious world. From Earth, even through powerful telescopes, Uranus appears as little more than a pale greenish-blue dot. It's just barely visible to the naked eye under perfect conditions, at the very limit of human vision, which is why it was overlooked for so long. Its apparent magnitude, the measure of its brightness as seen from Earth, hovers around 5.7. For comparison, the faintest stars most people can see under dark skies are around magnitude 6. Uranus sits right at that threshold, appearing as faint as the dimmest stars, easily lost in the vastness of the night. Among all the planets in our solar system, Uranus holds a distinction that makes it truly unique. While most planets spin like tops, with their poles pointing roughly up and down relative to the plane of their orbit, Uranus rolls through space like a ball. Its axis of rotation is tilted 98 degrees from the perpendicular. Imagine taking Earth and tipping it onto its side so that the North Pole pointed almost directly at the Sun. That's essentially what happened to Uranus. This extreme tilt means that Uranus experiences the most unusual seasons in the solar system. Picture this. For 21 Earth years, roughly a quarter of a Uranian year, one pole faces the Sun in constant daylight while the other pole sits in complete darkness. Then, as Uranus continues its slow 84-year orbit around the Sun appears to rise over the equator. For the next 21 years, the equatorial regions receive the most sunlight. Then the opposite pole tilts toward the Sun for another 21 years of continuous daylight while the first pole freezes in endless night. Think of it like a lighthouse lying on its side. As it rotates, its beam sweeps around the horizon rather than up into the sky. If you were standing on Uranus, depending on where you were and what season it was, you might experience 42 years of daylight followed by 42 years of darkness. The equatorial regions fare better, experiencing something closer to a normal day-night cycle, though even these regions endure wild seasonal variations. What could cause a planet to tip over like this? The most widely accepted explanation involves a collision early in the solar system's history. About 4 billion years ago, when the planets were still young and space was crowded with debris, something massive likely struck Uranus. This impactor would have been enormous, perhaps 1 to 3 times the mass of Earth. The collision didn't destroy Uranus but transferred enough energy and momentum to knock the planet onto its side. Think of it like hitting a spinning top with a baseball bat. The top doesn't stop spinning, but it might start wobbling or tilting at a crazy angle. Computer simulations suggest that such an impact could have occurred during the final stages of planet formation, when large bodies were still careening through the solar system, occasionally slamming into one another in catastrophic encounters. Some scientists propose an alternative scenario. Perhaps it wasn't one massive collision but several smaller impacts over time. Like a boxer taking multiple hits, each blow could have tilted Uranus a bit more until it eventually rolled onto its side. Another hypothesis suggests that gravitational interactions with other giant planets during the solar system's youth might have contributed to the tilt, though this alone probably couldn't account for such an extreme angle. Whatever the cause, this sideways orientation has profound effects on the planet. The unusual heating pattern, with poles receiving more sustained sunlight than the equator over time, creates strange atmospheric dynamics. You might expect the pole pointing at the Sun to be much hotter than the rest of the planet, but measurements show that the equator and the sunlit pole have similar temperatures. Somehow, heat is being redistributed around the planet, though scientists are still working to understand exactly how this happens. The tilt also affects Uranus's magnetic field in peculiar ways. While Earth's magnetic field is roughly aligned with its rotation axis, Uranus's magnetic field is tilted 59 degrees from its rotational axis and offset from the planet's center. As Uranus rotates, its magnetic field wobbles like a misaligned spinning magnet. This creates a chaotic, corkscrew-shaped magnetosphere unlike anything else in the solar system. Charged particles from the Sun spiral into this twisted magnetic environment, creating auroras that appear in unexpected places, sometimes near the equator rather than near the poles as they do on Earth. Uranus belongs to a category called ice giants, a term that distinguishes it from the larger gas giants Jupiter and Saturn. But don't let the name fool you. The ice giant doesn't mean frozen water as you'd find in your freezer. Instead, astronomers use ice to describe materials that were in solid form in the cold outer regions where these planets formed. These include water, methane, and ammonia, substances that exist in various states throughout Uranus's interior. Imagine peeling back the layers of this distant world like an onion. At the very top, we encounter the atmosphere, the only part of Uranus we can directly observe from Earth and visiting spacecraft. This atmosphere extends down about 6,000 miles and consists primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Hydrogen makes up roughly 83% of the atmosphere, while helium accounts for about 15%. But it's the remaining 2% that gives Uranus its distinctive color. Methane, that simple molecule made of one carbon atom bonded to 4 hydrogen atoms, pervades the upper atmosphere. Methane has a peculiar property. It absorbs red light but reflects blue and green light. When sunlight streams through Uranus's atmosphere, the methane filters out the warmer colors, leaving only the cool blue-green hues to bounce back into space. This is why Uranus appears as a serene, cyan sphere when viewed through telescopes. Descending deeper into Uranus, we pass through the atmosphere into what scientists call the mantle, though it's unlike any mantle you'd find on a rocky planet. This region, extending perhaps 12,000 miles down toward the core, is where things get truly strange. Here, water, methane, and ammonia exist under such extreme pressures and temperatures that they form what's known as a supercritical fluid, a state of matter that's neither quite liquid nor quite gas. Think of it like this. Normally, water can be ice, liquid, or steam depending on temperature and pressure. But if you squeeze water hard enough and heat it enough, it reaches a point where the distinction between liquid and gas disappears. It becomes a supercritical fluid, flowing like a liquid but expanding to fill space like a gas. In Uranus's mantle, these materials exist in this bizarre state, sloshing and swirling in the planet's interior. The pressures in this region are crushing. At the top of the mantle, pressures might be a few 100,000 times Earth's atmospheric pressure. Deeper down, near the core, pressures could reach 6 million times Earth's surface pressure. To give you a sense of scale, that's like having the weight of 250 fully loaded semi-trucks pressing down on every square inch of surface. No submarine, no deep-sea vessel humanity has ever built could withstand even a tiny fraction of such pressure. Temperatures in the mantle likely range from around 3,000 to 9,000 degrees Fahrenheit. Hot enough to melt rock on Earth, yet here these materials remain in their supercritical state because of the immense pressure holding them together. This hot, electrically conductive fluid might be responsible for generating Uranus's unusual magnetic field. Convection currents in this layer, combined with the planet's rotation, could drive the dynamo that produces the magnetism, though the details remain uncertain. At the very center of Uranus, there may be a small rocky core, perhaps half the mass of Earth. This core would be composed of silicate rock and iron, the heavy elements that sank to the center during the planet's formation. However, the line between the core and the mantle above it probably isn't sharp. Instead, there's likely a gradual transition zone where rock and the supercritical fluids mix. When Voyager 2 flew past Uranus in 1986, scientists were surprised by what they didn't see. The spacecraft's cameras revealed a nearly featureless pale blue sphere. Unlike Jupiter with its dramatic swirling storms and colorful bands, or even Neptune with its great dark spot, Uranus appeared calm, almost boring. Only a handful of clouds were visible, faint wisps against the uniform blue-green atmosphere. This apparent tranquility led some to conclude that Uranus was a quiet, inactive world. But appearances can be deceiving. The Voyager encounter happened to occur during Uranian spring, when one pole was pointing almost directly at the Sun. This unusual geometry might have suppressed atmospheric activity. As seasons changed and better telescopes came online, astronomers began to see that Uranus was far more dynamic than first thought. The atmosphere of Uranus is divided into layers, much like Earth's atmosphere has its troposphere, stratosphere, and so on. The lowest layer, the troposphere, is where weather happens. This region extends from the top of the cloud layer down to where temperatures and pressures increase enough that we transition into the mantle below. In the troposphere, temperatures vary from around -370 degrees Fahrenheit at the top to slightly warmer temperatures deeper down. Clouds form in the troposphere at different altitudes depending on which compounds are condensing. The deepest clouds, made of water ice mixed with ammonia, form at the highest pressures. Above these lie clouds of ammonium hydrosulfide. Higher still, methane condenses into icy crystals, forming the bright white clouds occasionally visible from Earth. These methane clouds appear as bright spots against the deeper blue atmosphere because they reflect sunlight before it can be absorbed. Winds on Uranus are surprisingly fast. At the equator, atmospheric measurements show winds blowing up to 560 miles per hour. That's faster than the most powerful hurricanes on Earth and comparable to wind speeds on Neptune. These winds blow in the same direction as the planet's rotation, though scientists aren't entirely sure what drives them. On gas giants, heat from the interior typically powers atmospheric circulation. But Uranus emits very little internal heat compared to the other giant planets, making its powerful winds something of a mystery. Think of a pot of water on a stove. Heat from the bottom creates convection currents that cause the water to circulate. The giant planets work similarly, with internal heat driving massive circulation patterns in their atmospheres. But Uranus's stove is barely on. The planet radiates only about 1.1 times more heat than it receives from the Sun, far less than Jupiter or Saturn. Why, then, does it have such energetic winds? One possibility involves the unusual seasonal heating pattern caused by that sideways tilt. As one pole bakes in decades of sunlight, energy accumulates in that hemisphere. When seasons change and that energy starts redistributing around the planet, it might drive atmospheric motion. Another factor could be the depth to which sunlight penetrates. Uranus's relatively clear atmosphere allows sunlight to reach deeper layers where it can be absorbed and converted to motion. Storms on Uranus come and go. In 2006, astronomers observed a dramatic increase in cloud activity as Uranus approached its equinox, the point in its orbit where the sun shines directly on the equator. Bright clouds appeared at various latitudes, and a dark spot resembling Neptune's Great Dark Spot briefly appeared in the northern hemisphere. These features suggest that Uranus's atmosphere is capable of producing dramatic weather systems, even if they're not always visible. Temperature is another puzzle. Despite receiving one pole's worth of continuous sunlight for decades at a time, measurements show that Uranus's equator and its poles have similar temperatures. The planet must have some mechanism for transporting heat from the sunlit regions to the dark ones. Atmospheric circulation probably plays a role, but the details remain unclear. Despite being only the seventh planet from the Sun, not the eighth like Neptune, Uranus holds the title of coldest planet in our solar system. Its cloud tops can plunge to a frigid -371 degrees Fahrenheit, colder than Neptune even though Neptune orbits the Sun about 1 billion miles farther out. This counterintuitive fact reveals something fundamental about how planets retain and radiate heat. All of the giant planets in our solar system formed hot. The process of assembly, with countless smaller bodies crashing together and releasing their gravitational energy as heat, left these worlds with scorching interiors. Over billions of years, this primordial heat has been slowly leaking out into space. Jupiter still radiates about 1.7 times more energy than it receives from the Sun. Saturn radiates about 1.8 times more. Even distant Neptune emits roughly 2.6 times the solar energy it absorbs. But Uranus is different. It radiates only slightly more heat than it receives from the Sun, barely more than a planet with no internal heat source at all. It's as if someone turned off the furnace inside Uranus, leaving it to cool in the depths of space. The question of why this happened haunts planetary scientists. One hypothesis returns us to that ancient collision that may have tipped Uranus onto its side. Perhaps the impact did more than just knock the planet over. Maybe it was violent enough to disrupt the planet's interior structure in ways that affected how heat moves through the planet. Think of insulation in a house. If you compress it or disrupt it, heat might not flow through it the same way. Similarly, if the impact jumbled Uranus's interior, it might have affected how efficiently heat can travel from the deep interior to the surface. Another possibility involves the distribution of materials inside Uranus. If heavier elements didn't fully settle into distinct layers during formation, the interior might have a more uniform composition than other giant planets. This could affect convection, the process by which hot material rises and cool material sinks, carrying heat from the interior to the surface. With less efficient convection, heat might be trapped in the deep interior, unable to escape. There's also the chance that Uranus did cool down more than its siblings during the early solar system. If it formed with less initial heat or lost heat more efficiently when it was young, it would have less stored thermal energy to radiate away today. Time acts as an insulator in a sense. The longer heat has to travel from the core to the surface of such a massive planet, the more it cools along the way. Whatever the reason, this lack of internal heat has profound effects. It makes Uranus's atmosphere more stable and less turbulent than it might otherwise be. Without strong heat rising from below to drive convection, the atmosphere doesn't churn as vigorously as those of Jupiter or Saturn. This might explain why Voyager 2 saw so few clouds and why the planet appeared so uniform. The cold also affects the chemistry of the atmosphere. At such low temperatures, many compounds that would be gases on warmer worlds condense into ices. Methane freezes out of the atmosphere at higher altitudes than it would on Neptune, affecting cloud formation and atmospheric structure. The extreme cold creates conditions found nowhere else in the solar system, a natural laboratory for studying matter at the edge of what's thermodynamically possible. For comparison, the coldest temperature ever recorded on Earth was negative 129 degrees Fahrenheit at Vostok Station in Antarctica. Uranus's cloud tops are more than 240 degrees colder than that. It's colder than the surface of Pluto during parts of that dwarf planet's orbit. It's so cold that if you could somehow stand in Uranus's upper atmosphere, many gases we think of as normal, nitrogen, oxygen, carbon dioxide, would be frozen solid. When we think of planetary rings, Saturn immediately comes to mind with its spectacular, bright bands visible even through small telescopes. But Saturn isn't alone. Jupiter, Uranus, and Neptune all possess ring systems of their own, though far subtler and more difficult to observe. Uranus's rings were discovered quite by accident, through an event that showcased the cleverness and persistence of astronomical research. In March of 1977, astronomers were preparing to observe Uranus pass in front of a distant star. These events, called occultations, provide valuable information about a planet's atmosphere. As the planet moves between Earth and the star's light passes through the planet's atmosphere before being blocked entirely. By carefully measuring how the starlight dims and changes color, scientists can deduce properties of the atmosphere it passed through, like temperature, pressure, and composition. Several teams of astronomers, including one aboard a special airplane called the Kuiper Airborne Observatory, pointed their instruments toward the predicted path of the occultation. They began their observations early, wanting to catch every moment as Uranus approached the star. About 35 minutes before Uranus itself was due to block the star, something unexpected happened. The starlight briefly dimmed, flickered, and then returned to normal. Then it happened again. And again. 5 separate dips in the star's brightness occurred, each lasting just a few seconds. At first, scientists weren't sure what they were seeing. Some wondered if the measurements were errors or if perhaps Uranus had previously unknown moons. But as they continued watching, the same pattern of dips repeated after Uranus had passed the star, but in reverse order. The symmetry was striking and pointed to only one conclusion. Uranus had rings, and the starlight had been blocked as it passed behind these thin, dark bands of material. This discovery was revolutionary. Before 1977, Saturn was thought to be unique in possessing rings. Now Uranus joined that exclusive club, and soon after, rings would be found around Jupiter and Neptune as well. It turned out that rings might be common features of giant planets. Uranus has 13 known rings, each given names rather than numbers. The inner rings are named Alpha, Beta, Gamma, Delta, and Epsilon in order of their discovery and distance from the planet. Later observations revealed additional rings, including the broad, faint Mu and Nu rings, and eventually the extremely faint outer rings named Zeta, 6, 5, 4, and Gamma. The naming system is admittedly confusing, a consequence of discoveries spread over decades by different research teams. The rings of Uranus are nothing like Saturn's brilliant displays. They're dark, reflecting only about 2% of the sunlight that hits them. This makes them incredibly difficult to see. The material in these rings is thought to be mostly water ice mixed with some darker substance, possibly radiation-processed organic compounds or rocky material. Over time, radiation from the sun and cosmic rays bombards the ice, darkening it and turning the rings into the charcoal-colored bands we observe. Think of fresh snow compared to old city snow that's been driven through and polluted. Fresh snow is brilliant white, reflecting most light that hits it. Dirty, old snow is gray and dingy, absorbing more light than it reflects. Uranus's rings are like that old snow, darkened by eons of exposure to space. The rings are also remarkably narrow. The Epsilon ring, the brightest and most substantial of the system, varies in width from about 12 to 60 miles. For comparison, that's narrower than the distance across many cities. Saturn's main rings span thousands of miles in width. Yet despite being so narrow, the Epsilon ring extends all the way around Uranus in a nearly perfect circle. What keeps these rings so narrow? On their own, rings tend to spread out over time. Particles collide, some speed up and move to higher orbits, others slow down and move to lower orbits, and gradually the ring becomes broader and more diffuse. But Uranus's rings stay confined. The answer involves shepherd moons, small satellites that orbit just inside and outside the rings. Their gravity nudges wayward ring particles back into line, much like a shepherd dog keeps a flock of sheep together. Two such moons, Cordelia and Ophelia, were discovered by Voyager 2 flanking the Epsilon ring. Their gravitational influence keeps the ring particles corralled. Similar dynamics probably shape the other rings, though not all shepherd moons have been found yet. Some may be too small to have been detected. Uranus doesn't journey alone through the outer solar system. It's accompanied by at least 27 known moons, a diverse family of worlds ranging from tiny captured asteroids to substantial spheres large enough to have their own geological histories. Unlike most moons in the solar system, which are named after figures from Greek and Roman mythology, Uranus's moons take their names from characters in the works of William Shakespeare and Alexander Pope. This literary tradition gives the Uranian system a distinctive character. The five largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were all discovered through telescopes from Earth between 1787 and 1851. William Herschel, who discovered Uranus itself, also discovered the first two moons, Titania and Oberon, in 1787. He spotted them as faint points of light near the planet, moving in ways that indicated they were bound to Uranus by gravity. Titania, the largest of Uranus's moons, measures about 980 miles in diameter, roughly half the size of our own moon. Its surface is a tapestry of craters, canyons, and ridges, suggesting a violent past. The Messina Casamata, a canyon system on Titania, stretches for nearly 1,000 miles, cutting deep into the moon's icy crust. This enormous crack hints at internal forces that pulled the moon apart, perhaps caused by the freezing and expansion of a subsurface ocean early in its history. Imagine water freezing in a bottle. As it turns to ice, it expands, and if the bottle is sealed, it might crack or even burst. Something similar might have happened to Titania. If it once had a liquid water ocean beneath its icy surface, the gradual freezing of that ocean would cause the interior to expand, fracturing the surface and creating the canyons we observe today. Oberon, the second largest and outermost of the major moons, also bears the scars of impacts and internal activity. Its surface is heavily cratered, testament to billions of years of collisions with debris. But some craters on Oberon have dark material on their floors, possibly a mixture of ice and carbon-rich compounds that erupted from the interior when impacts punched through the surface. This suggests that Oberon's interior was once more active, perhaps warmed by radioactive decay or tidal heating. Ariel presents perhaps the most geologically young surface of the major moons. Its terrain is crisscrossed with valleys, faults, and ridges, and it has fewer craters than Titania or Oberon, suggesting that geological activity has resurfaced parts of Ariel more recently. Valleys on Ariel appear to have been filled with some kind of material, possibly ice that flowed like a very slow liquid or slushy mixture that oozed across the surface. Scientists call this cryovolcanism, a type of volcanism where the lava is water, ammonia, or other substances that are liquid or slushy at the frigid temperatures of the outer solar system. Umbriel, in contrast, appears ancient and dark. Its surface is the darkest of the five major moons, reflecting only about 16% of the sunlight that strikes it. Umbriel is heavily cratered with few signs of recent geological activity. One feature stands out, a bright ring about 90 miles across called the Wonder Crater. This unusually bright feature on an otherwise dark moon remains something of a mystery. It might be a relatively recent impact that exposed fresher ice, or it could be deposits of bright material transported from elsewhere on the moon. And then there's Miranda, the smallest of the five major moons, but perhaps the most bizarre. When Voyager 2 captured detailed images of Miranda in 1986, scientists were stunned. The little moon, only about 290 miles in diameter, displayed a chaotic jumble of terrain unlike anything seen elsewhere. Enormous faults cut across its surface. Strange polygonal regions called coronae, areas of grooved and ridged terrain, sit alongside heavily cratered plains. One feature in particular captured attention: Verona Rupes, a cliff that drops nearly 3 miles down, the tallest known cliff in the solar system. To give you a sense of scale, that's about 15 times taller than the walls of the Grand Canyon. Due to Miranda's weak gravity, if you could somehow jump off Verona Rupes, you'd fall for about 12 minutes before hitting the ground, plenty of time to contemplate your decision. Miranda looks like it was taken apart and reassembled. One theory suggests that the moon was indeed shattered by a massive impact and then reformed from the pieces. The story of humanity's exploration of Uranus is brief but remarkable, centering on a single spacecraft that ventured farther from home than any mission before it. Voyager 2, launched in August of 1977, was part of an ambitious plan to visit the outer planets during a rare alignment that occurs only once every 176 years. This alignment allowed a spacecraft to use gravity assists, stealing a tiny bit of momentum from each planet it passed to slingshot onto the next destination. Voyager 2 first flew past Jupiter in July of 1979, then Saturn in August of 1981. Each encounter provided gravitational boosts that sent the spacecraft deeper into the solar system. By the time Voyager 2 approached Uranus in January of 1986, it had traveled for more than 8 years and covered over 1,700,000,000 miles. The spacecraft carried a suite of instruments including cameras, spectrometers, magnetometers, and radiation detectors. Engineers and scientists had designed these instruments in the 1970s, before modern computers and electronics. The entire spacecraft communicated with Earth using a transmitter powered by about 23 watts, less power than a typical refrigerator light bulb. Yet this faint signal had to travel nearly 2 hours at the speed of light to reach Earth. On January 24, 1986, Voyager 2 made its closest approach to Uranus, passing within 50,000 miles of the cloud tops. During its brief encounter, the spacecraft discovered 10 new moons, confirmed the existence of the ring system, measured the planet's magnetic field, and captured hundreds of images. But the encounter was challenging. Uranus was so distant and dim that exposure times for photographs had to be long, and the spacecraft had to be precisely positioned to avoid blurring. The images revealed a world of subtle beauty. The pale blue-green globe, nearly featureless in visible light, hinted at hidden complexity. The moons, especially Miranda, proved far more interesting than expected. The discovery of the tilted, offset magnetic field raised new questions about the planet's interior. And the detailed measurements of temperature, composition, and atmospheric structure provided data that scientists continue to analyze decades later. After Uranus, Voyager 2 continued to Neptune, its final planetary encounter, before heading out into interstellar space where it travels still, now more than 12 billion miles from home. No spacecraft has returned to Uranus since. The ice giant remains one of the least explored planets in our solar system, visited only once during a brief flyby. But that may change. In recent years, planetary scientists have advocated strongly for a dedicated mission to Uranus. In 2022, a major scientific review by the National Academies of Sciences recommended that NASA prioritize a Uranus orbiter and probe as its next large planetary mission. Such a mission could spend years studying the planet, watching how its atmosphere and magnetosphere change with seasons, examining the moons in detail, and perhaps even sending a probe plunging into the atmosphere to measure its composition directly. questions abound that only a new mission could answer. What lies beneath those tranquil cloud tops? How does heat move through the planet's interior? Do any of the moons harbor subsurface oceans that might support some form of life? What caused the unusual magnetic field? How do the rings maintain their structure over billions of years? What is the detailed composition of the atmosphere, and are there complex organic molecules forming in those frigid clouds? Understanding Uranus also helps us understand planets beyond our solar system. Many planets discovered orbiting other stars are similar in size to Uranus and Neptune. These Neptune-mass planets appear to be common throughout the galaxy. By studying Uranus in detail, we gain insights into how such planets form, evolve, and behave. Each discovery at Uranus informs our understanding of thousands of worlds light years away. There's something humbling about Uranus. It reminds us how much we don't know, how many mysteries remain even in our own celestial neighborhood. Here is a world we've known about for more than 240 years, yet we've spent fewer than 6 hours examining it up close. It orbits in the dim outer reaches of our solar system, patient and enigmatic, waiting for humanity to return with better instruments and deeper questions. And on that note, we conclude our peaceful exploration of Uranus, that sideways giant rolling through the darkness. We've journeyed from its accidental discovery to its icy moons, from its peculiar magnetism to its shadowy rings, from the mysteries of its formation to the possibilities of future exploration. Thank you for joining me on this voyage through the outer solar system. I hope you found some wonder in these distant, frozen realms, and perhaps some peace in contemplating the vastness and strangeness of our cosmic home. Neptune's discovery in 1846 represents one of the most elegant achievements in the history of astronomy. Unlike the planets known since ancient times, Neptune was found not by accident or systematic searching, but through the power of mathematical prediction. This story begins with Uranus, the seventh planet, which had been discovered in 1781 by William Herschel. After Uranus was found, astronomers carefully tracked its motion across the sky, comparing their observations with predictions based on Newton's laws of gravity. Everything should have worked perfectly. The mathematics of gravity had already proven themselves by predicting the motions of all the other known planets with remarkable precision. But Uranus refused to cooperate. It wandered slightly off course, arriving at positions in the sky earlier or later than calculations suggested it should. By the 1830s and 40s, these discrepancies had become impossible to ignore. Uranus was straying from its predicted path by amounts that exceeded any reasonable measurement error. Two possibilities existed. Either Newton's laws of gravity broke down at such great distances from the Sun, or something else was out there, an unseen planet whose gravity was tugging on Uranus and altering its orbit. Two mathematicians, working independently on opposite sides of the English Channel, chose to believe in an unseen planet. In England, John Couch Adams performed calculations to determine where such a planet might be located. In France, Urbain Le Verrier did the same. Both men worked backward from the observed irregularities in Uranus's motion, using gravity's mathematics to predict where the hidden world must reside. Le Verrier finished his calculations first and sent his predictions to Johann Galle at the Berlin Observatory. On September 23, 1846, Galle pointed his telescope to the patch of sky Le Verrier had indicated. Within an hour of searching, Galle found Neptune, less than 1 degree away from its predicted position. The planet had been found with mathematics before it was found with eyes. This discovery validated not only Newton's laws, but also demonstrated the profound power of mathematical reasoning. Here was proof that the universe operated according to principles humans could understand and predict. The success of finding Neptune through calculation alone inspired astronomers to believe that other hidden worlds might exist, waiting to be discovered through similar methods. Think of it like hearing a note in music you cannot quite identify. You know the sound exists because you hear it, but you cannot see what instrument creates it. By understanding how different instruments produce different tones, you could deduce which instrument must be playing even without seeing it. This was Neptune's discovery, a cosmic note identified by its gravitational influence before anyone had actually laid eyes on the instrument creating it. The finding of Neptune pushed the known boundary of our solar system outward by more than 1 billion miles in a single night. It transformed our understanding of the Sun's family from 7 planets to 8, and it showed that even in the vast darkness of space, nothing truly hides from mathematics. When you look at images of Neptune, the first thing you notice is its color. The planet glows with a deep, rich blue unlike anything else in our solar system. Even Uranus, Neptune's near twin in size and composition, appears as a much paler, greenish blue. Neptune's vivid color comes from methane in its atmosphere, but there's more to the story than simple chemistry. Sunlight contains all the colors of the rainbow mixed together. When this light reaches Neptune, it encounters an atmosphere made primarily of hydrogen and helium, with a small amount of methane mixed in. Methane molecules absorb red light very efficiently while allowing blue light to pass through or scatter back into space. This selective absorption means that the light bouncing back from Neptune toward our telescopes and cameras is predominantly blue. However, scientists have discovered that methane alone cannot fully explain Neptune's intense blue color. Uranus has roughly the same amount of methane in its atmosphere, yet it appears much paler. Research published in the past few years suggests that another substance, possibly a haze of photochemical products or another compound formed high in the atmosphere, enhances Neptune's blueness. The exact identity of this additional component remains a subject of ongoing investigation. Neptune's atmosphere extends thousands of miles deep, gradually becoming denser as you descend. Near the top, where space begins, the air is thin and hazy. Deeper down, the atmosphere becomes thicker, forming distinct cloud layers at different altitudes. Some of these clouds are made of methane ice crystals, similar to how Earth's clouds are made of water ice and liquid droplets, but existing at temperatures that would freeze any water solid in an instant. The planet's appearance changes depending on the altitude and thickness of these cloud layers. High-altitude clouds appear as bright features against the darker blue background, while lower clouds seem darker. The Hubble Space Telescope has captured images showing bright, white methane clouds casting shadows on the deeper cloud layers below them, revealing the three-dimensional structure of Neptune's atmosphere. Temperature plays a crucial role in creating these cloud layers. At the very top of Neptune's atmosphere, temperatures drop to around -360 degrees Fahrenheit. This extreme cold would freeze almost any gas, turning it into ice crystals. As you descend, temperatures gradually increase due to the mounting pressure of all the gas pressing down from above. Imagine descending into an ocean, but instead of water, you are moving through an ocean of gas that slowly becomes thicker and thicker. Near the surface of Earth's ocean, you can see light filtering down from above. Deeper down, the water takes on a blue-green tint, and eventually, all light fades to darkness. Neptune's atmosphere follows a similar pattern, though the details differ dramatically. Instead of water blocking light, you have layers of methane haze and clouds, and instead of a solid seafloor, You eventually reach a transition zone where the gas becomes so dense and hot that it behaves more like a liquid. The blue we see is thus a message from Neptune's upper atmosphere, a specific signature created by the chemistry and physics occurring in those highest, coldest layers. Every photon of blue light that reaches our eyes has survived a journey through Neptune's atmospheric filter, carrying information about the composition and structure of this distant world. That vivid blue is not just beautiful. It's a scientific treasure containing clues about the planet's nature. Despite its name, Neptune is not actually made of ice as we typically think of it. When astronomers classify Neptune as an ice giant, they're referring to a definition of ice that differs from frozen water in your freezer. In planetary science, ices are materials that freeze at relatively low temperatures, including water, methane, and ammonia. Inside Neptune, however, conditions are so extreme that these materials behave in ways entirely unlike ordinary ice. Neptune's interior structure consists of three main regions. The outermost layer is the atmosphere we've already discussed, extending down several thousand miles and making up only a small fraction of the planet's total mass. Below this lies a vast mantle of hot, dense materials sometimes called the ice layer, though calling it ice is misleading. Here, under immense pressure and at temperatures reaching several thousand degrees, water, methane, and ammonia exist in exotic states of matter. Think of it like this: if you squeeze water hard enough and heat it sufficiently, it stops behaving like either liquid water or solid ice. Instead, it becomes something in between, a superionic state where oxygen atoms form a crystalline structure while hydrogen atoms flow through that structure like a liquid. These conditions exist deep within Neptune, creating materials with properties we're only beginning to understand. The mantle extends down about 8,000 miles from the cloud tops and contains most of Neptune's mass. The pressure here reaches millions of times Earth's atmospheric pressure. At such pressures, methane breaks apart into carbon and hydrogen. Some scientists propose that the carbon atoms then bond together under the extreme conditions to form diamond crystals. These diamonds would sink slowly through the surrounding material like snow falling through air, except this snow would be made of gemstones drifting through hot, dense fluids. Laboratory experiments have attempted to recreate these conditions using powerful lasers and diamond anvils that squeeze tiny samples to extreme pressures. These experiments have confirmed that diamond formation is possible under Neptune-like conditions, lending support to the idea of diamond rain in the planet's interior. However, directly observing this phenomenon remains impossible with our current technology. At Neptune's core lies a region roughly the size of Earth, composed of rock and metal heated to temperatures around 9,000 degrees Fahrenheit. This core formed first in Neptune's history when the young planet pulled together from the swirling disk of material that surrounded our infant Sunday. The immense pressure at the core, about 8 million times Earth's surface pressure, keeps the rock and metal compressed into a dense sphere. One of Neptune's most puzzling characteristics is that it radiates about 2.6 times more energy into space than it receives from the Sun. Jupiter and Saturn also emit more energy than they receive, but their heat comes primarily from leftover warmth from their formation, still slowly leaking out after billions of years. Neptune lost most of its formation heat long ago given its smaller size and greater surface area to volume ratio. So where does this extra energy come from? The most widely accepted explanation involves differentiation, the process where heavier materials sink toward the center while lighter materials rise. As heavier substances descend through Neptune's interior, they release gravitational potential energy that converts into heat. This ongoing process, happening imperceptibly slowly by human standards but continuously over eons of time, generates enough warmth to power Neptune's heat output. This internal heat source drives the fierce storms and powerful winds that characterize Neptune's weather, creating atmospheric dynamics far more energetic than the weak sunlight alone could sustain. Neptune possesses the most violent winds known in our solar system. These jet streams race through the planet's upper atmosphere at speeds exceeding 1,000 miles per hour, far faster than any hurricane on Earth and even faster than the speed of sound in Neptune's thin upper atmosphere. Understanding why such extreme winds exist on a world that receives so little energy from the sun has challenged planetary scientists. Earth's winds derive their energy primarily from solar heating. The sun warms the equator more than the poles, creating temperature differences that drive air circulation. Neptune, however, receives less than 1,000th the sunlight that Earth does, making solar heating seem insufficient to power such energetic winds. Yet Neptune's winds blow with ferocity that dwarfs anything in our experience. The answer lies in Neptune's internal heat. As we discussed, the planet radiates more than twice as much energy as it receives from the sun. This heat flowing up from the interior provides the primary energy source for Neptune's atmospheric dynamics. Imagine a pot of water heated from below. The water at the bottom warms up, becomes less dense, and rises, while cooler water descends to take its place, creating circulation patterns. Neptune's atmosphere works similarly, but on a planetary scale and with far more energy available. The winds on Neptune blow primarily in an eastward direction, the same direction the planet rotates. However, some jet streams flow westward, moving opposite to the rotation. The fastest winds occur in the southern hemisphere around 30 degrees south latitude, where wind speeds regularly exceed 1,200 miles per hour. To put this in perspective, Earth's fastest winds, found in the jet stream, typically reach around 200 miles per hour. Neptune's rapid rotation contributes to organizing these winds into distinct bands. The planet completes one rotation in about 16 hours, spinning quickly enough that the Coriolis effect, which deflects moving air, becomes very strong. This effect helps organize atmospheric circulation into east-west bands at different latitudes, similar to but more extreme than the bands visible on Jupiter and Saturn. In 1989, when Voyager 2 flew past Neptune, it observed several large storms. The most prominent was the Great Dark Spot, an Earth-sized storm system similar to Jupiter's Great Red Spot. This dark oval rotated counterclockwise and drifted westward relative to Neptune's overall rotation. Bright white clouds, likely methane ice crystals, formed around the edges of the storm where air rose and cooled. Interestingly, when the Hubble Space Telescope observed Neptune 5 years later, the Great Dark Spot had vanished. However, a new dark spot had appeared in the northern hemisphere. Since then, astronomers have observed several dark spots come and go, suggesting that unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's large storms are transient features lasting only a few years. Think of Neptune's atmosphere as an engine powered from within rather than from above. The internal heat provides a steady flow of energy that rises through the atmosphere, creating instabilities that grow into massive storm systems and drive the high-speed winds. The weak sunlight contributes some additional energy and creates subtle temperature variations between day and night, summer and winter, but the internal heat dominates the energy budget. These winds accomplish something remarkable. They mix and homogenize Neptune's atmosphere, distributing heat and chemical compounds across different latitudes and altitudes. This mixing helps maintain the planet's uniform appearance and relatively simple banded structure compared to the more chaotic patterns seen on Jupiter. Neptune takes 165 Earth years to complete a single orbit around the Sun. This means that each season on Neptune lasts approximately 41 years. If you were born during Neptune's summer, you would be middle-aged before autumn arrived. This extreme seasonal length creates atmospheric changes that unfold on timescales vastly different from anything we experience on Earth. Like Earth, Neptune has seasons because its rotation axis is tilted relative to its orbital plane. Neptune's axis tilts at about 28 degrees, slightly more than Earth's 23.5 degree tilt. This tilt means that during Neptune's northern summer, the North Pole points more directly toward the Sun and receives more sunlight, while the South Pole spends more time in darkness. 41 years later, the situation reverses. However, Neptune's seasons are peculiar for several reasons. First, because Neptune is so far from the Sun, the seasonal variation in sunlight is less dramatic than you might expect. The Sun appears as merely a bright star in Neptune's sky, about 900 times dimmer than it appears from Earth. Whether that dim star shines more directly on the northern or southern hemisphere makes only a modest difference in the amount of energy received. Second, Neptune's internal heat source partially masks seasonal effects. While Earth's weather and climate are driven almost entirely by solar heating, Neptune's atmosphere receives most of its energy from below. This internal heat source doesn't vary with seasons, providing a constant background of energy that moderates seasonal temperature changes. Despite these factors, astronomers have detected seasonal changes on Neptune. Observations from the Hubble Space Telescope spanning several decades show that Neptune's southern hemisphere, which has been experiencing summer, has gradually brightened. More high-altitude clouds have appeared, suggesting increased atmospheric activity. Meanwhile, computer models predict that as Neptune's seasons progress, patterns of cloud formation and storm activity should shift between the hemispheres. The seasonal changes also affect Neptune's moons, particularly Triton, the largest. Triton has its own thin atmosphere and, being tidally locked to Neptune, it experiences seasonal changes based on Neptune's position in its orbit. As different parts of Triton receive varying amounts of sunlight over Neptune's long year, ice sublimates from warmer regions and condenses in colder ones, slowly redistributing material across Triton's surface. Observing seasonal changes on Neptune requires patience and dedication. A graduate student who begins studying Neptune's seasonal variations at the start of their career would need to continue observations for their entire professional lifetime to witness the transition from one season to the next. This presents both challenges and opportunities for astronomers. The challenge is maintaining consistent observations over many decades. The opportunity is that Neptune provides a laboratory for studying atmospheric dynamics operating on timescales much longer than typical weather patterns on Earth. Think of watching plants grow. If you check hourly, you see no change. But watching daily or weekly reveals their gradual development. Neptune's seasonal changes occur on an even longer timescale, and visible day to day or even year to year, but becoming apparent when observations span decades. The slow pace of Neptune's seasons also means that each hemisphere spends decades at a time experiencing similar conditions. The storms, winds, and cloud patterns we observe today represent a snapshot of Neptune's southern summer, conditions that have prevailed for decades and will continue for decades more before autumn's gradual transition begins. Future generations of astronomers will witness Neptune's atmosphere transform as the seasons progress, comparing their observations with ours and building an understanding of how this distant world changes through its long year. Neptune possesses a ring system, though these rings are so dark and tenuous that they remained undetected until the Voyager 2 spacecraft flew past in 1989. Unlike Saturn's brilliant rings, which reflect sunlight so efficiently that they outshine the planet itself when viewed edge-on, Neptune's rings are faint and ghostly, composed of material darker than charcoal. The ring system consists of 5 main rings, each named after scientists who contributed to Neptune's discovery or study: Gale, Leverrier, Lassell, Arago, and Adams. The innermost ring, Gale, is faint and broad, beginning about 2,500 miles above Neptune's cloud tops. The outermost ring, Adams, lies about 39,000 miles from the planet's center and displays the most interesting structure. Adams' ring contains several bright arcs rather than forming a uniform ring. These arcs, given names like Liberté, Égalité, and Fraternité, appear as bright clumps of material concentrated in specific sections of the ring. When these arcs were first detected from Earth before Voyager 2's arrival, astronomers were puzzled. Ring material should spread out evenly around a planet due to the varying orbital velocities at different distances. What could hold these arcs together? The answer involves gravitational resonances with Galatea, a small moon orbiting just inside the Adams ring. Galatea's gravity creates a pattern of stronger and weaker gravitational pull at different points around the ring. Particles in the ring move slightly faster or slower depending on their position relative to Galatea, and this causes them to bunch together in specific locations. Think of it like people walking around a track at slightly different speeds. Most of the time they spread out, but if something periodically gives them a gentle push, they might bunch together at certain points. Neptune's rings are incredibly dark, reflecting only a few percent of the light that hits them. They appear to be made of material rich in organic compounds, perhaps similar to the surfaces of some asteroids and comets, which have been darkened by exposure to radiation and the solar wind over billions of years. The particles making up the rings range in size from microscopic dust grains to boulders several yards across. Several small moons orbit among and near Neptune's rings. These moons, including Naiad, Thalassa, Despina, and Galatea, are all irregularly shaped and relatively tiny, with diameters ranging from about 30 to 100 miles. They orbit Neptune in less than a day, racing around the planet at speeds of several miles per second. These inner moons probably formed from material left over after Neptune itself formed, material that gradually coalesced into these small bodies. Some of these small moons may act as shepherd moons, using their gravity to help confine ring material and prevent it from spreading out or falling into the planet. However, Neptune's ring shepherding appears less efficient than Saturn's. The rings are quite diffuse and seem to be relatively young in geological terms, perhaps only a few 100 million years old rather than as ancient as the planet itself. Occasionally, collisions between small moons or between moons and larger particles may shatter these bodies, creating debris that replenishes the rings. Without such replenishment, the rings would gradually fade away as particles spiral into Neptune or are knocked out of orbit by various perturbations. The existence of the rings today suggests that this replenishment process continues, with small moons slowly grinding themselves away to create the ghostly rings we observe. Triton, Neptune's largest moon, is one of the most fascinating worlds in our solar system. About 2,000 miles in diameter, roughly 3/4 the size of Earth's moon, Triton orbits Neptune in the opposite direction that the planet rotates. This backward or retrograde orbit immediately tells us something remarkable. Triton did not form alongside Neptune. Instead, this moon was captured, pulled from an independent orbit around the Sun into servitude around Neptune billions of years ago. In the solar system's early days, The region beyond Neptune contained countless icy bodies, remnants of the planet-forming disk that never coalesced into a major planet. This population still exists today as the Kuiper Belt, though it has been greatly depleted over time. Triton likely originated as one of these Kuiper Belt bodies, possibly similar to Pluto, before a gravitational encounter with Neptune millions or billions of years after the planet's formed caused it to be captured. The capture process was violent. Triton would have approached Neptune on some arbitrary trajectory, and through a combination of gravitational interactions, possibly involving other moons or bodies that no longer exist, it lost enough energy to become bound to Neptune. Initially, its orbit would have been highly elliptical and tilted at a random angle. Over hundreds of millions of years, tidal forces gradually circularized the orbit and, crucially, converted the orbital energy into heat within Triton's interior. This tidal heating was intense. Imagine repeatedly flexing a piece of metal back and forth. It becomes hot from the internal friction. Triton experienced this on a planetary scale as Neptune's gravity flexed and squeezed it during each orbit. This heating likely melted Triton's interior completely, causing the moon to differentiate into a rocky core surrounded by a thick mantle of liquid water and other ices. The surface may have been an ocean for a time before cooling and freezing into the icy crust we see today. Modern Triton is a frigid world with surface temperatures around -390 degrees Fahrenheit, making it one of the coldest surfaces in the solar system. Yet this frozen moon is geologically active. When Voyager 2 flew past in 1989, it observed geysers erupting from Triton's surface, blasting plumes of nitrogen gas and dark organic particles up to 5 miles high. These plumes then drifted downwind in Triton's thin atmosphere, creating dark streaks across the icy plains. The geysers likely formed through a greenhouse effect. Sunlight penetrates Triton's relatively clear nitrogen ice crust and warms darker material beneath the surface. The nitrogen ice at depth absorbs this heat and sublimates, turning directly from solid to gas. As pressure builds, the gas eventually breaks through weak points in the crust and erupts as a geyser. Think of a pressure cooker where steam builds up until it finds a release valve. Triton's surface displays diverse terrain. Some regions are covered with smooth plains of frozen nitrogen, while others show cantaloupe terrain, a unique landscape of oval depressions and ridges unlike anything seen elsewhere in the solar system. Still, other areas preserve signs of ancient geological activity, including what appear to be frozen lakes and possible cryovolcanoes that erupted slushes of water and ammonia rather than molten rock. Because Triton orbits Neptune backward, tidal forces continue to act on it, but now they remove energy from the orbit rather than circularizing it. This means Triton is very slowly spiraling inward toward Neptune. In a few billion years, Triton will cross the Roche limit, the distance at which Neptune's gravity will tear it apart. When this happens, Triton will be destroyed, and its material will spread out to form a spectacular ring system around Neptune, far more impressive than the modest rings that exist today. Every detailed image of Neptune, every measurement of its atmospheric composition, every discovery about its rings and moons, comes from a single spacecraft encounter lasting only a few hours. On August 25, 1989, Voyager 2 became the first and, so far, only spacecraft to visit Neptune, flying within 3,000 miles of the planet's cloud tops during its final planetary encounter after a 12-year journey through the outer solar system. Voyager 2 approached Neptune from below the ecliptic plane, the imaginary sheet on which most planets orbit. This trajectory allowed the spacecraft to study Neptune's atmosphere, rings, and magnetic field before making its closest approach. The spacecraft's cameras captured images showing the Great Dark Spot, bright methane clouds, and the banded structure of the atmosphere. Instruments measured temperature, pressure, and composition at different levels of the atmosphere and detected Neptune's offset magnetic field, which is tilted 27 degrees from the rotation axis and offset from the planet's center. After passing Neptune, Voyager 2 flew within 2,500 miles of Triton, capturing the only close-up images we have of this fascinating moon. These images revealed the geysers, the varied terrain, and the incredibly smooth surface with very few impact craters, suggesting recent geological resurfacing. Then Voyager 2 departed, heading out of the solar system on a trajectory that will never bring it close to another planet. Since 1989, all our observations of Neptune have come from telescopes on Earth and in Earth orbit, primarily the Hubble Space Telescope. These observations have tracked seasonal changes, monitored the formation and disappearance of dark spots, and studied variations in Neptune's brightness and color. However, telescopic observations have limits. Even Hubble cannot resolve details smaller than a few hundred miles across on Neptune, and spectroscopic measurements from such distances provide only bulk averages of atmospheric composition and temperature. Many questions remain unanswered. What causes Neptune's vivid blue color to be so much more intense than Uranus's? What is the exact structure and composition of the interior? How do the winds maintain such high speeds? What drives the formation and dissolution of the large dark spots? How does Triton's geology work in detail, and what might liquid layers exist beneath its frozen crust? Several mission concepts have been proposed to return to Neptune. One idea involves an orbiter that would spend several years studying the planet, watching seasonal changes unfold, mapping the magnetic field in detail, and repeatedly flying past Triton and the other moons. Another concept suggests a probe that would descend into Neptune's atmosphere, measuring temperature, pressure, and composition directly as it falls through the cloud layers before being crushed by the increasing pressure. Such missions face significant challenges. The journey to Neptune takes at least 12 years with current propulsion technology. The immense distance means communication signals take more than 4 hours to travel each way between Earth and a spacecraft at Neptune. The weak sunlight at Neptune's distance makes solar panels impractical, requiring spacecraft to use nuclear power sources. These factors make missions to Neptune expensive and technically demanding. Yet the scientific rewards would be profound. Understanding Neptune helps us understand how giant planets form and evolve. The planet's internal heat source, powerful winds, and active moon system raise questions relevant to the study of planets around other stars. Many of the thousands of known planets orbiting other stars appear to be Neptune-like worlds, making our ice giant a crucial reference point for understanding planetary systems throughout the galaxy. For now, Neptune remains mysterious, visited once and watched from afar, its secrets guarded by distance and time. And on that note, we reach the end of our peaceful journey to Neptune. We've traveled nearly 3 billion miles from home to explore a world of deep blue clouds and 1,000-mile-per-hour winds, a planet that generates its own heat and wears a set of dark, ghostly rings. We've descended through layers of atmosphere where the pressure grows intense enough to form exotic states of matter and perhaps to rain diamonds from compressed methane. We've witnessed storms the size of Earth that appear and vanish over the course of years, and we've considered seasons that last longer than most human lifetimes. We explored how Neptune was discovered through mathematics before it was seen with human eyes, a triumph of prediction that extended the known solar system by more than 1 billion miles in a single night. We learned why Neptune glows with such a vivid blue color, deeper and richer than any other planet, a hue created by methane in its atmosphere and enhanced by substances we're still working to identify. We examined the planet's interior structure, that strange realm where ices behave as liquids and carbon atoms may crystallize into falling diamonds. We marveled at winds that race faster than the speed of sound through an atmosphere powered not by sunlight but by heat rising from below. We contemplated the glacial pace of Neptune's seasons, each one stretching across 4 decades, creating atmospheric changes that unfold on timescales requiring generations of astronomers to observe. We discovered rings made of material darker than coal, held together by the subtle gravitational influence of small shepherding moons. And we met Triton, the remarkable captured moon that orbits backward and erupts geysers from its frozen surface despite being one of the coldest places in our solar system. We learned that Triton is slowly spiraling toward Neptune and will one day be torn apart to form a magnificent ring system far grander than anything surrounding the planet today. Perhaps most remarkably, we recognize that all our detailed knowledge of Neptune comes from a single spacecraft encounter lasting only a few hours more than 35 years ago. Since then, we've watched from afar, tracking changes through telescopes but unable to return for a closer look. Neptune holds countless mysteries still waiting to be explored, questions that will require future missions and future generations of scientists to answer. Neptune reminds us of the vastness of our solar system and how much remains to be discovered. This distant world, spinning in near darkness at the edge of the planetary realm, conducts its own grand experiments in atmospheric physics, planetary geology, and celestial mechanics. Every measurement we make, every image we capture, adds another piece to the puzzle of how planets work and how our solar system came to be. Thank you for joining me on this exploration. I hope you found it peaceful and perhaps even learned something new about this distant ice giant. Whether you're drifting off to sleep or simply enjoyed some time contemplating the cosmos, I'm grateful you chose to spend this time with the nocturnal astronomer. If you have thoughts about Neptune or suggestions for future topics you'd like me to cover, please leave them in the comments below. And if you enjoyed this journey, remember to give it a thumbs up and subscribe so you won't miss future explorations. Until next time, keep looking up.